speaker, can you? Thank you. Morning, Ilya. How are you doing today?
Yeah, hi Renee, I'm good. And you?
Excellent, thank you. Good to see you. Thank you very much for yesterday. Okay, Alawani, do you want to? Good morning.
Morning, everyone. Yes, welcome to today's session. So this is the last session. We're going to have some, I can quickly share the timetable. Yes, so if you check, this is the last
timetable 11.
Yeah, so we're going to have some changes. So we're going to have a lunch break at 1 o'clock to 2 o'clock, and then we're going to have the closure for today at 2 o'clock. Yes, and then I think we can start. And welcome and all the best. Over to you, Prof.
Okay, so good morning, everyone. So where we are with classification? Have anybody changed the code for the regressor to classifier for the wine classification? Okay. I know that's. So I repeat my question. Have anybody done change of the yesterday's notebook, change of the random forest regressor to random forest classifier? Okay, what can we do? Okay, so there are honest confessions that no, but usually, if it was yes, I assume that there was much more yeses in the chat. Okay, so what is our plan for today? In that case, let me share the lecture notes. Or maybe, yeah, I mean, let me quickly make the note with a classifier visible because it's already in the canvas, so that at least you can try to go through the code. Oops. So now it's visible in the canvas and it's called advanced example wine CLF. CLF obviously for classifier. And yes, so I suggest that you guys go through that. So I can quickly share my screen and show you without running it. Yeah, I already provided the solution. For RAG and LLM, somebody asked for the good recommendation. There are sequence of the short courses by deep learning AI, I think they call it. Just give me a sec. Oh, deep. Yes. These guys have a bunch of short courses which are free. So you don't have to take a paid specialization, but there is a whole bunch of short courses where you can learn some basics of interaction with LLMs and things like that. And okay. Oops, what's happening in the chat? Okay. Somebody is writing attempted but got all the predictions for the same one. I'm not really sure that I understand your answer, Natasha, because what do you mean? Yes, you can get the predictions. What do you mean the same predictions? You cannot get the same predictions because the measuring ways will be different. Because, you know, you cannot calculate MSE and things like that. You need to calculate accuracy, confusion matrices, and things like that. Because kind of like if you treat it as a classification problem, so if you treat the problem as classification problem, so essentially I just took the same notebook, which we have yesterday, and we treat it as regression. And let me just go directly to, okay, is it the right notebook? Just, I think it's not that one which I uploaded to the chat, but doesn't matter because we're interested in this bit. So we have 7 classes, but now we need to do the random forest classifier, not regressor. And we need to use the entropy as a criterion for the building of the, and we can play the game. And it's essentially the same, but the thing is what is changing is how we score the things. And we can score the things, for example, using accuracy, or you can play with some other types of scoring. And of course, on the trained data, it's trained perfectly and the confusion matrix is perfect. But you already could see the possible problems that, you know, for the class of Mark 3, you have very little, and the Mark 9, you have very little even training data. Not, I mean, and even short, smaller the test data, which wouldn't be nice for the any kind of for any machine learning problem. And that's exactly what we see when we plot the confusion matrix. You see in the confusion matrix, in the test data, we get even kind of like worse results. So we get it a little bit all over the place, but essentially one can play the same game, but now we need to change the score into accuracy and accuracy score. And we can do the same grid search and find the optimized parameters for classification. And essentially, yes. And interestingly enough, it's also, of course, change the weightings of the features and which are important, which are not important, but more or less they are in the same ballpark, but otherwise, yeah. So go through the notebook. I think I zoomed in already. Do I need to? I think that was before 9:37. Do I need to zoom in more? Okay, but just go through the notebook. It's now visible in Canvas because I uploaded yesterday, so it should be yes here, this one, and treat classification as classification problems. Okay, and now let's go to the today's theoretical bit, and afterwards we'll go to the today's experimental bit. Okay, so yesterday we spoke with you a little bit with the generic structures of the what kind of machine learning we're dealing with and what it could be. So we spoke a little bit about the supervised learning, but we never really, and we spoke about regression and classification, and but we haven't spoke about unsupervised learning, and we finished with those kind of the decision trees and random forest, and in principle in the nodes, it's also going into the, you know, how the ensembles, you know, how you build from the trees, the forest, not just by simple, there are different ways. So you can just do it by the kind of majority vote, or you can do it in a little bit smarter way, let's put it this way. And so there are different ways of, so you can build so-called boosting trees, but with the lack of time, let's skip it and let's go to the one piece which is very important, which is called dimensionality reduction. Or I just want to tell you a few words about what is a kind of the way where you can have a principal component analysis or some nonlinear analogs of that, and which could be extremely useful. And what we'll go afterwards, we'll go into the neural nets, and I will give you a very basic introduction to that stuff. And afterwards, kind of like after the break, we are going to go through the tutorials. And that would be it. And so what is dimensionality reduction? So as we've seen, very often what we're dealing with very large. So we're dealing with very large, kind of a lot of features in your input data. And but even as we've seen with the examples, some features are important, or some entries of your matrices are important, and some entries are not important. And when you need to do it at scale with a kind of a lot of data, every saved every saved feature is a useful thing if you can get good enough precision. Okay, so and within the unsupervised learning, it's one of the approaches which is called dimensionality reduction, which essentially allows you to create effective representations with the small dimensionality. Okay, so yes, because it's also going back to the question, when the people was asking how to choose the features. So, and that's where it's coming in. So we need to reduce the complexity. Yes, we need to remove the kind of the correlated features, if the features behave the same. So maybe you can take into account only one feature. Yeah. So, or remove the kind of useless features and so on and so forth. Okay. So there will be an epsilon of mathematics, but essentially what it is boiling down to is, you've seen already metrics like this, and we need to think about this metrics that we know the rows are entries of our machine learning problem, so that each one input one by one, and the n is the number of inputs. Yeah, and so one could think about as the kind of as the representations for the metrics, or for the kind of in some vector space. And the question is like, can we reduce the dimension of that vector space? And essentially, I think we can a little bit be faster with mathematics and more focus on the intuition behind the dimensionality reduction. So, for example, if we can consider a two-dimensional case and we have a points like that, from the normal perspective, kind of like x and y axis, or x1 and x2, we see that the points are distributed in some way. But if we imagine that we could clearly see that, in fact, the points are not distributed all over the, xy plane or x1, x2 plane, they're more distributed along the diagonal. And essentially, you can explain most of the behavior of the points if you just go along the diagonal. Of course, the orthogonal direction to that is also important, but not as this kind of diagonal. And that is essentially the idea behind what is called this principal component analysis. So it means that, this will be the primary axis along which you need to introduce your new coordinates. And this will be kind of the extra axis, which can do the kind of extra smaller details. And you can imagine the same approach works in many, many dimensions. And what you can find out that for the given problem, essentially, instead of 100 dimensions, there is 3 or 4 important dimensions. And you just need to go to that. You need to go systematically and ideally without too much of doing it by hand and seeing on the pictures, but doing it in an automatic way, in a programmatic way, into that new picture, saying that, okay, all the features whose kind of like importance and what does it mean we're going to see just now is too low, we can just stick to the most important ones, and that might be good enough for our machine learning problem. Or what also sometimes you can do, you can add it as the extra features to your problem, which can probably explain your data, which can improve the explanation of your data. Oops. Okay, so Okay, so let's skip a little bit of mathematics. And for those of one who is interested, you can ask questions. But this is just, a very simple, and mathematically, it's all boiling down to the simple singular value decomposition, essentially. Okay, so let's skip it, and let's go directly to the meaning. Okay, so and the meaning, as I mentioned to you, is exactly like that. So that so this will be the first principal component which explain the most diversity in the data, and that would be the second component which if this component is too small, you can just essentially throw it away, and this is the intuition behind it. And of course, mathematically, you want to explain the most. You need to explain the most variance in the data. And ideally, what is traditionally done. So what you want to stick to, you want to explain 90% of the variance in the data, and all the rest you kind of throw away. Essentially, those components which explain all the rest tails, you throw away, or you can keep it. But you can decide. I mean, this is up to you as the person who is designing machine learning algorithm, where you go and how much you keep the data. Okay. So the standard PCA algorithm is looking like, so you have given a data, you form the data matrix, you need to compute the data mean, you need to subtract the mean from each row. Afterwards, you construct the covariance matrix, which will be D by D, and afterwards you find its eigenvalues. But essentially what you do kind of underneath, you just do, I mean, first of all, Python will do, or scikit-learn will do it for you automatically. Yes, and for this matrix, you find the eigenvalues, you order them in the kind of the greatest on the top and the smallest on the bottom range, and afterwards you just decide where you want to cut, and that will create for you the effective representation for the data. Okay, so for example, you have something like this, so you get a feature importance, and the first feature explain 22% variance of the data, second this one, and kind of it's slowly decreasing, so that on some stage you can say that, okay, after this point I'm not interested anymore because I could explain the most of the variance in the data by these components. So it's mean that instead of, for example, 10-dimensional space, you can stick to the 5-dimensional space. Or something like that. So kind of like this is a typical approach how you deal with that. And in fact, when you have a very large data, it's very rare that you have some reasonable value all the way through. So it's really very often that typically it will go down quite fast, and afterwards you have a very kind of very small values which you can really easily throw away. And this is very typical approach, not only for the things like principal component analysis, but there are a lot of numerical techniques which are used, for example, in physics and also in mathematics to approximate your kind of the vectors in the spaces, give a smaller representation. Okay, so, and essentially one could try to play this game on some visualization. So when you kind of, and also nice thing is that, you can use, if you start from the large data set and you can try to bring it to, some sort of 2-dimensional representation or 3-dimensional representation, you can very nicely visualize data because, of course, sometimes you have you need to have a 5 or more principal component, but unfortunately we cannot think in 5 dimensions, although some people claim they can, but usually it's very difficult to imagine. So what you can do, you can use it for the visualization, and the principal component analysis, one could think that it's some sort of linear transformation of your space. So it's really, you just rotate to the eigenvalues and eigenvectors or eigenvalue basis, and you just choose, certain number of the largest eigenvalues which you are going to keep, and all the rest you throw away. But again, what we also kind of like, what we're going to see in the tutorial, that is going to be done automatically for us. And we can now try to visualize, and the standard game with visualization, what can we do? We can try to visualize the digits. So the digits is the standard, one of the standard data sets, and the task is to recognize which digit is written. It's a multi-class classification problem with the 10 classes, yes, from 0 to 9. And PCA will do the job like this. The typical PCA would do the job like this, which is not nice, because this is quite nonlinear data, but in some other data sets, it works nicely. And essentially, there are So PCA works, but in some cases, and the usual recommendation is that you try and you see if it works or not. And if it works, you use it, and if it doesn't work, you use some other ways. And I'm now going to mention the other ways just now. Yes, and you can use this principal component analysis as a pre-processing step for many supervised learning models. So to reduce dimensionality, to reduce the correlated features, and sometimes it could be used for visualization. So what you can do beyond PCA, so when PCA is not working, so there are the similar game, but it's nonlinear transformations. And again, for any practical purpose, we don't even need to understand, how it works. I mean, of course, if you're interested to understand what exactly it's doing, you're welcome to do it. But for us, it's just another module in Python. And for example, I think there will be an example in the tutorial with TSNE, which is stochastic nonlinear embedding. So it's doing something like PCA. It's doing rotation, but it's doing it with some nonlinearities. And it's a standard thing that, with the TSNE, you can take the digits data set and it will map it into dimensional space in the blobs like that. And these blobs are already much more separable. Yes, you can see that, okay, that would be one digit, that would be another digit because the color corresponds to the classes of digits. And so TSNE and ISOMAP are powerful methods which use nonlinear mappings, okay? But sometimes it's a little bit longer to compute because PCA is extremely popular and used as a pre-processing tool just because, it's very easy to compute, it's very fast, and, half of or kind of a lot of machine learning problems when the people doing the pre-processing, they're doing PCA on the components. Okay. And so that's all what I wanted to tell you about these dimensionality reduction techniques. Because kind of like we're a little bit, don't have too much time, so just very quickly, but just, in the tutorial we're going to see, it's really very straightforward. So we just have our data set, and as we yesterday done the transformation with standard scalar, when we're scaling the data, we can do the PCA transformation fit and apply to our data. Okay, so now let's speak quickly about the neural nets. Okay. Okay, so a brief history of some famous things. So there was a perceptron model first. It's kind of a very, very simple neural network, and scikit-learn can do that thing as well, but nothing more. And that's why, for the neural nets, we're going to use more specialized packages. And I suggested to use TensorFlow. Somebody was complaining in the chat that, why not PyTorch? It doesn't really matter. If you know PyTorch, you can do all the same in a PyTorch. And this is just a matter of, just randomness, essentially. So as you see, it's kind of the very basic model is extremely old. It's 1943. So McCulloch and Pitts. And afterwards, there was some implementations. And afterwards, there was a realization that the simple perceptron cannot XOR. But afterwards, it was realized how to do it. So it can learn, but not a simple perceptron. Afterwards, there was some essentially advancements in the 80s. And essentially what was very interesting and kind of like, because it was all nice and it was happening, but there was not much happening in reality for a very long time because there was not enough computational power. And only because these convolutional neural nets were invented, there was also an algorithm how to train neural networks were invented, but it was all not a large scale stuff. But what happens seriously, that happens in 2012, and this is a crucial event for the neural nets, because what happens over there, that there was a realization, and we're going to discuss it, that the way how to train the neural networks is the algorithm which is called backpropagation algorithm, which is kind of like a fundamental algorithm. And what was realized is that we can do that backpropagation extremely efficient, then you can map backpropagation to the matrix multiplications. So that's the first. And the second thing, which was extremely important, is that by the beginning of 2000s, the gaming industry was developed so much so that they begin to require from the hardware manufacturers to produce a highly efficient graphic cards to play games. But what is the playing of the games, like, 3D shooters and things like that? You need to simulate the physical world of the game. And that implies the simulation of the physical world involves a lot of matrix multiplication. Essentially, gaming industry developed or create a huge demand on the hardware industry to develop objects or kind of the pieces of hardware which can extremely efficiently multiply matrices and do it at scale. And when the people realize that you can do the same things which are used for gaming, that you can use it for backpropagation. So what happens over there? So that one can now start doing the convolutional neural networks, and you can train it on the large scale data, on the graphical cards. And in 2012, ImageNet there was a breakthrough on ImageNet with ImageNet as a competition where you have, a lot of images with the different classes. I think it's around 1,000 classes. And there was all sorts of algorithms more in the style as we were discussing before. They were trying, and they were having really like a marginal improvement in the overall accuracy. So it's like every year plus 1%, roughly speaking. And after it was realized how to train convolutional neural networks using graphical cards, there was like 10% improvement in accuracy. And that was the architecture which is called AlexNet. And afterwards it was clear so that the way to do the very high scale classification tasks, and not only classification tasks, is to train these structures which are called convolutional neural networks at scale on the graphical cards. And afterwards it was up to the races. And so after 2012, all the ImageNet competitions were successfully won by the corresponding more and more involved neural net architectures. And that's why we're here in the age of AI. Okay, so if 2012 is a breakthrough for the convolutional neural networks, 2017 was another very interesting architecture is suggested, which is called transformer architecture. And this is a special kind of neural networks which allows you to train on the sequential data, but it allows you to train it with the long range correlations. And what does it allow you to do? It allows you very nicely to do the text processing. And it allows you, so essentially all the successes of the modern OpenAI models or ChatGPT models or similar ones are based or were originally based on this some kind of advanced version of that transformer architecture. And essentially, so that's what is happening. Yes, and of course there is in 2018 there was a Turing Award which was awarded, and this is Computer Science Award to the Benjo, Hinton, and LeCun. But if you also read the newspapers, you know that the Hinton also get a Nobel Prize in physics in 2024, and exactly for the same things. Okay, so what was the reasons? As I mentioned to you, the GPUs. Also, another reason is development of the internet. So for the images, we have an internet with a lot of images. For the text processing, we have a lot of internet with the textual data. Yeah. And of course, in the moment when you have an advancement in the hardware, you need to have a corresponding algorithm developing. So we get the better algorithms which can accelerate the training, and so on and so forth. Yes, and kind of like, and there is an accumulation, what is used here is called folk knowledge, but you can think about it's accumulation of this thumb rules. So people were training the larger networks, and they've seen that this way works. It's not really clear why it works, but this way works better. Because multiple experiments are telling you, okay, this way works. Okay, it's mean that, okay, you need to go this way. Okay, and of course, in the moment when the development of the neural networks seriously go from the universities to the private companies, it's also added extra scale to the problem. Can we combine transformer architecture with CNN? It is combined in some sense. Okay, no. So let's speak about the model family, because we're far away in this lecture from the transformers, and we're not going to talk about them. And if you have questions like that, I suggest to ask ChatGPT, because ChatGPT knows more things than I. Okay. So what is a neural network? Very simply, the neural network, and now you should be a little bit disappointed, because there is a standard family for the neural networks. It's called feed-forward neural network. And what is this formula? This is again good old linear model, and this is the simplest neural network. But the difference is that we have our entrance x, we multiply it by some metrics, which we'll need to discuss what it is. And afterwards, we apply some function. So in some sense, it's a feature space transformation. And now afterwards, applied some vector. And that's all. And this is the simplest possible neural network. And this is perceptron model, essentially. And this is kind of very, very simple feed-forward neural network for regression problem, because this thing will spit you out number from whatever range from a real number. And what we need to learn how to train it. And who is who here? So your data have a dimension, have obviously D entries. Yeah, so your x have a D entries. So your W is a matrix D by K. So when you multiply matrix D by K by vector with the D entries, yes, we're going to get a vector of the dimension K. Yeah. And afterwards, we apply nonlinear function to every element of that vector, and multiply it with another vector of K entries. And what we get as a result, we get number. Okay. So, and this G have a special name. It's called activation function. And it's applied component-wise. So G applied to the vector Z1, Z2 is G of Z1, G of Z2. And the example of the activation function, which you're aware of, or which we've seen already, is a sigmoid function. And in fact, this is very commonly used function for the neural networks, but there are several other choices. Okay, so yes, sigmoid, we've seen it already yesterday in logistic regression and in the classification. Okay, so, and how we can imagine it. So we have entries x1, x2, x3. We multiplied by corresponding entries w's and apply the activation function g. So we form the new set of values. And afterwards, we multiply it by beta. So we get beta on vector z. We get the result. So, and this layer of this is called input layer. This is called output layer. And this is called hidden layer in this case, because it's one, but you can have, as we're going to see, many of them. And that's where the power of the neural networks are. Okay. So if function g is linear, obviously we're getting linear functions. Yeah. So if g is identity, we're just getting good old linear functions, and we can just quickly go on. So, but using nonlinearities is very important. Why it's very important? Because, so let me just go back to here. So there is a mathematical statement which is telling to you, so that even such a simple neural network, but if you allow to grow in the number of the neurons in the hidden layer, could learn any function. So any mathematical function could be learned using the perceptron. And this statement is called universal approximation theorem. So, and that automatically tells you, and there is no statement like this, for example, about linear regressions and other old style neural net or other old style machine learning algorithms. And that is kind of a very good indication why neural networks have already from the start kind of an advantage, because for them, you can formulate the statement which is telling you exactly that any function could be learned using this simple perceptron model, or this very simple neural network. Okay, so if we want to play the classification game, it's very simple. Yes, we just need to remember so that we have a likelihood function like that yesterday. So what we can do we can just put here perceptron and afterwards apply the same rule. Yeah. Oops. So we put here perceptron, and afterwards, if it's above 1/2, it's one class. If it's below 1/2, it's a different class. And multi-class classification, exactly in the same way. So what we do here, we do softmax. You remember yesterday we have the softmax, e to the beta z1, e to the beta z2, e to the beta z3 divided by the sum. So that will be the probabilities. So out of the box, neural networks can do essentially everything what neural models from yesterday can do. And as we know, the neural networks can do much more. Okay, so there is a historical view on neural networks and there is a modern view. And the historical view is you start from the feed-forward network and you rediscover architectures. The modern view is a little bit more standardized and nicer, because it's just talking about, the neural networks is a thing which is constructed from the layers, and you just adding up the layers, and the layers could be different, and as a function of and you have a different connectivity between the layers, and as a function of which layers you are dealing with, you get different architecture. So kind of because all the neural networks, convolutional neural networks, transformers, and some other neural networks, they're all constructed out of the layers. But as a functions, which layers are using and what kind of connectivity you get the different architectures. Okay, so feed forward. And the feed forward network could be, kind of we can do it further. So we can add one more layer. Yeah, and we can rewrite it. Okay, we're still not adding one more layer. We just adding, sorry, a little bit mathematical notation. So this is a feed-forward network, but where we just separating the operations. Sorry, this is important. Yes, so because we have it like this, and this is in fact is a two operation. One is a matrix multiplication, and another is applying the nonlinear function. So for the convenience of the scaling, it's better to rewrite it like this. And this is just a rewriting, so that we can think of that, first we have an input layer, afterwards we do the linear multiplication, afterwards we do the nonlinear function, and afterwards we do again linear multiplication and nonlinear function if we need to. Okay? But what's happening in that case, that it's obviously clearly that we can just scale it up. So we can add here another layer of the matrix multiplications, another layer of the nonlinear functions, and so on, or another layer doing something else. And what is that something else we're going to see? So for example, we can add layer which is going randomly zero out one of the neurons in the layer, and we'll see why it could be interesting or why it could be important. Okay, so each layer is a function from previous layer dimension to the next layer dimension. Yeah, and we can just sequentially compose it. Yes, and this circle is a notation for the operation which is called composition, or just function of function of function. So function of function is just a composition of two functions. Okay, so let's skip that so that we don't scare anyone, and let's go to, yes, so we're here, and now we can denote it like that. Yes, so again we have input vector x. We apply the function which is doing multiplication for us. F of w is just doing matrix multiplication. We get vector of z's, and afterwards we apply a nonlinear function. We get z2, and after again multiplying by beta, we get in value y. Okay, so and if it's a classifier, we also add sigmoid. So we do y, but it won't be yet y. It will be some z3, and afterwards sigmoid, and we get our y as an answer. Okay. And interestingly enough, so that what do we have? W and beta are the only trained parameters because the nonlinear function g is fixed. And why it so makes sense, this a little bit of rewriting, you will see just now. Yes, so kind of like we have an input layer, we have all the internal structures are called hidden layers. Yeah, and the last layer is output layer. The parameters which we need to optimize are standardly called weights, and what is kind of the reason why we can train the neural network so efficiently is because we know how to map the process of training to the backpropagation algorithm, or kind of like that the training procedure will be done by the backpropagation algorithm, which is essentially showing that how to map all of this procedure in training into the matrix multiplication of for those W's and betas. Okay, so obviously, if we have two hidden linear layers and so on, so we have first we multiply on the matrix W1, we get vector Z1, we apply the nonlinear function, we get vector Z2, afterwards we multiply vector Z2 on the matrix W2, we get vector Z3, again apply nonlinear function, we get vector Z4, and afterwards we multiply that Z4 with vector beta, and we get our answer. And the idea is like, from the perspective of mathematics, or from the perspective also from the programming, it's just, a composable structure, which is very, very nice, because which you can grow in a standard way. So, and if you can show something for the smaller structures, it's also will work in the same way for the larger structures. It's just going to be recursively applied. Okay, so, and again, if you struggle a little bit with the circles, think about it's a function of function of function of function of function. Yes, so kind of like what is this guy is we take this x, we multiply it on W, apply nonlinear function to every entry, we get another vector, that vector will multiply on W2, apply another entry-wise nonlinear function, and finally we'll multiply it by the vector such that after all of that, we get some number. Okay, so pros and cons, very easy, yes, so that we can design a model families that we can in principle also, and especially that is important, for example, for an application for neural networks in science, so that you can incorporate symmetries of the problem, because many problems have asymmetries, and you can have a lot of parameters and you can train them. So problems is that, yes, it's really very hard to train. And, and the larger the neural networks get, the harder it's trained. And, sometimes, and it gets also more expensive to train. And yeah, there is plenty of design decisions, but also there are ways to work around it, but you need to have a lot of compute. Because you can apply, for example, people do things like genetic algorithms to design the neural network for your problem. But of course, in order to do things like that, you need to have a lot of computational power. Okay, so there are a couple of questions in the chat. Let me try to. A simple neural network computes input layer, one or more hidden layers, and the output layer. Simple neural networks is usually one hidden layer. Let's put it this one, and you're not necessary. I found. You can have Wx plus b, but in that case, you just need to add to your vector of entries one more entry. You're going to see why it's neural networks hard to train. We're coming to that. Okay, so let's go. Okay, so now what we need to do, we need to think about how we're going to train it or how we're going to optimize it. So we're going to use the algorithms because we know kind of that what is nice in training is gradient descent based. And so we wanted to do the gradient descent. But the problem is, and I think there should be a picture in these notes as well, of the example that now we don't dealing with a nice ball so that we need to go down the ball. No, now our landscape is very hilly and have a lot of little dips, and we need to make sure that our algorithm is not getting stuck in one of them. Yeah, and of course also the question is, how to compute nicely the gradient, and you need to compute the gradient of all of these more or less in one go, or you don't have to. But that's where the things are coming to. Yeah, so we need to work out the gradients, and we need to ideally came up with the way of systematic calculation of the gradients for the such structures. And the algorithm and the training algorithm is called backpropagation, and that's what we're going to discuss now. Okay, so gradient descent, again, let me remind it to you, but it's kind of like it's the same gradient descent that we used to have in the linear model. So in the last lecture, so we do it until convergence. So we have some our kind of values of our weight matrices or matrices which we multiply, and also W naturally here include also beta, and we need to calculate gradient with respect to the corresponding entry. Yeah. And what we need to do afterwards, we need to go in the opposite direction with some learning rate. And we do it until we converge. Okay, so what the algorithm is, we start from we have an example, we have some model, which we set it up. We calculate the loss function for the predicted value and the true label. So, and afterwards, we need to calculate the derivative. And now that's where the things are coming. And that's what we're going to see now, that the way that by the choice of our model families and the fact that it's a linear multiplication plus nonlinear function, but not arbitrary nonlinear function, but of nonlinear function of a certain kind, together with together with the standard product rule, or kind of the differentiation of the composite function, we can do it at scale. Okay, so we need to calculate, in principle, we need to calculate a derivative, and we need to calculate derivatives like this. Yeah, and the output should give us gradient. Okay, so for that, we need to do a little bit of math, but very quickly. So how to calculate derivatives in the multiple dimensions. So we have a function fw of z, and the fw of z, what is the fw of z? Is just a w, you can think here as a vector, and the input vector. No, why it's RD? No, this is supposed to be a matrix. Yes, this is supposed to be a matrix. Yes, this is supposed to be a matrix. Yeah. Okay, so and the derivative of the matrix multiplied by the value will be, with respect to the corresponding value, will be just corresponding value. And now we're going to see. So let's go into, yes, okay, so we have our function, we need to calculate the derivative, and the intuition is like this. So because we're dealing with the linear functions, so it's very simple and straightforward. Okay, so what we're dealing with, so we're using the gradient of MSE loss, because this is, again, for regression, it's a standard choice. So we need to calculate the gradient with respect to our weights, W and beta, of things like this. Yeah, so how we calculate, it's just a standard product rule. Yes, 2 on this, on the derivative of that. With betas, we get the same thing. Okay, and now where the power is coming from. Now, when we need to calculate the derivative with respect to our trainable parameters, we're differentiating complex function, yeah? So the derivative with respect to the beta of this is derivative of beta on everything else. What will be the derivative with respect to the W? It's a derivative with respect to the beta, or derivative with respect to the W of this composition. We need to do a derivative of all of that on the derivative of next internal thing. And derivative of this will be the derivatives of sequential derivatives. So it's a standard derivative of the composition, which I assume all South African students are supposed to learn in the first year calculus. And now, what we need to remember, where I mentioned where the power is coming from, that when we're taking a derivative of nonlinear function, derivative of g, we know, for example, if we use sigmoid, the derivative will always look the same. Yes, or if we use some other activation functions which are coming later. Yeah, and when we are calculating derivative with respect to the W or with respect to the beta, we're taking a derivative of linear function. We're taking derivative of matrix multiplied by vector with respect to the matrix entries, or with or derivative of the entries of the vector beta multiplied by the other vector z with respect to the entries here. And this is also linear multiplication, so that we can explicitly write without calculating, or we can write analytical expression. And afterwards, we need to play with that expression and see what are we getting. So, and that's where the kind of, although we need to calculate the gradient, we can do it in a systematic way without, kind of recalculating it every time. Okay, so how it's happening? So we start from the neural network. We have, m layers of whatever nature, and we need to introduce intermediate step. So, we apply to x w1 blah 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 until wj, and we're going to get zj. So, and if it's j is 0, we're in the initial point, and if j is 1, it's just, f of w applied to the previous z. Okay, so now we just sequentially apply the product rule. So if we need to do the derivative with to the layer m, it's just here, yes, because it's just derivative to the layer m of the function to the layer m minus 1. What's happening to the m minus 1? It's a derivative to the layer m because of the rules of composition on derivative of the layer m minus 1, which we also can calculate, and so on. So, and the idea is very simple, that it's really, you can calculate all these derivatives in the fully analytical way. Okay, so in derivative to some arbitrary layer j is just, you just take a composite derivatives until the layer j. Okay, so we can introduce some temporary notations that the portions shared, but also what you need to remember, so that, when we are calculating this derivative, we're calculating all of these intermediate derivatives, but when we need to calculate the derivative with respect to this guy, we still need to calculate all of that. And what does it mean? It means that we don't need to calculate it. We just need to calculate it once per go in propagation. So we calculate the derivative with respect to every layer, and afterwards we can store this information and use it to calculate exactly the gradients with the corresponding layers with the information stored. We don't need to recalculate it every time after time again. So because we already have done it. Okay, so we can compute it recursively, and you can just think about like this. What is the backpropagation? So we take your x, we multiply by w, we get one vector, we apply nonlinear function, we get processed vector, multiply by another matrix, we get vector, again nonlinear function, get vector, multiply by the vector beta, get our answer. So this is a forward path. So this is, we get an input, we get output. Now we need to calculate gradients. So we're calculating the derivative with respect to each of the layers, but for this value of input. And we are storing the values. So we are starting the forward propagation. So we have x, we get z1, afterwards we get z2, z3. So we get the answer, and afterwards we calculate it back. We calculate this d5. Oops, sorry. And we're saving the values of the corresponding derivative because we have it as a matrix. And d beta. So we go to the layer d4 and save the values. And we have to automatically know how to calculate the gradients, and we automatically have this information of the values of the gradients of the corresponding matrices. Okay? So, and if it's a little bit mathematical for some of you, just don't worry, because, again, we don't need to do it manually. We're not writing it from the scratch, because TensorFlow and the PyTorch or any other package is doing the backpropagation automatically for us. Okay? So, and we do this gradient descent until convergence. Okay? So, this is very simply and very briefly how the backpropagation works. And the idea is really, because of that composition, and because of the fact that we can really, we differentiate linear function. We just give you a coefficient in front, yes, because derivative of ax is just a, yeah, or derivative of ax with respect to the a is just x in this case. And we differentiate in well-known nonlinear functions. So instead of recalculating it, if we need to calculate the derivative of sigmoid, you can calculate it explicitly and you will get the function. Or if you calculate the derivative of the tanh function, which is another activation function, or ReLU, we can do it in advance and incorporate in our code. And from this perspective, there is no real calculations of all of this thing. It's just, building the compositions. Okay. So let's speak about how optimization is happening. And so that's a picture which I want you to keep in mind. And this is already an old picture, is that why the training of neural networks is hard, because this is an example, and this is a 2-dimensional or 3-dimensional example of the loss landscape. And, in reality, your loss landscape is not 3-dimensional. It's multi-dimensional. So, and if you are stuck somewhere here, you will never get here if it's a global minimum. Yeah. So if you're stuck somewhere there, you need to find the way, or you need to, in the way how you do the training, you need to have the way how you can get out of there and get into here. And, we see only the part of this landscape. So we don't even know, is it is it good enough or not, or is it a global minimum or not? I mean, maybe it's just, in the larger scale of things, it's not a minimum. Okay. So another problem, which is especially important for this kind of landscape are called non-convex landscape. So if somebody is telling you about the non-convex loss, you can imagine this. Convex loss will be, one ball-shaped. And what you also have, because, we calculate these gradients, yeah, and we multiply essentially. You can rewrite it as a matrix multiplication, but afterwards, you get multiplying many matrices. If you have, kind of a large neural network, what's happening, what you can have, that you can have, you have a multiplication of a lot of very small numbers, or a lot of kind of not small numbers, but for example, if numbers is larger than 1, but if you have multiplied many of them, if you multiply small numbers, you get something very close to machine level 0. And you will stuck there, and this is called vanishing gradient. Or if you multiply numbers which just above 1, but if you multiply many of them, you will get infinity also very fast. Yeah. So, and that is called exploding gradients, and that's what people need to learn how to deal with. And as I mentioned to you, this there is a thumb rules, or sometimes it's called heuristics, which essentially which is boiled down to. So you need to do the training and see how it works. And if it works, you continue. And if it doesn't work, you go to Stack Overflow or Stack Exchange. You ask the question and people say, I've been doing this and it works. You go and try. And if it works, good for you. So this is your kind of additional rule of, of the summarizing of human experience. But with many basic things, there is already enough information on Stack Overflow and Reddit, or also probably ChatGPT also knows that by now because it's have it in its training data set. Oops. Okay, so what can you do with the gradient descent and how you can make it better? So what you can do, because here we need to sum over the whole data set, yeah? Because what is N? It's a whole data set of entries. But if you need to train, for example, if you have the 100,000 images, for every step, you need 100,000 calculations. And this could be quite costly. So what you can do, first of all, you can go from the gradient descent to what is called a stochastic gradient descent, where essentially what you can do the calculation on the subsets. And you can take the random subsets of the training data for training, or you can even split it into the smaller batches and go afterwards, kind of in some sort of average direction. And it's not perfect, but it's cheaper computation. And on the very large training, it's give you a very nice result. Another thing what you can do is as I mentioned, we have that learning rate. And you remember in the last yesterday, we have a lecture with a nice parabola. And if you have a too small learning rate, you're going down too slow. If you have a too high learning rate, you jump and you can even get out of your local minima. So what you can do, you can have you can add acceleration to your gradient descent. And when it's necessary, you can accelerate it. And when it's not necessary, you can slow it down. So, and this is the different types of the gradient descents, which one can use. And what you can also check that, in the standard packages, which are kind of like, TensorFlow or PyTorch, it support the whole family of the different forms of calculation of the gradients, or the way how you to do optimization. And this is parameter, it's called optimizer, and you tell which optimizer to use. Okay, so, and there is a kind of like intuition behind the accelerated gradient descent, which is really kind of, so if you remember the previous update, so you can calculate, you can have something like acceleration. Okay, so there is also Nestor of momentum, but again, from our practical purpose, you just you try the different optimizers, and if you see that they're working better, these ones are working better than that ones, you use those which works. I mean, by default, everybody is using Adam, but it's not always not always the best choice. Okay, and there is some intuition behind the Nestor of momentum. Okay, so what else you can do in optimization? So you can play with the learning rate directly. So you can use what is called the adaptive learning rate, so that, as I mentioned to you, so you can start with a larger learning rate, and afterwards you can decrease it. And you can do it in these forms as they're suggesting here, so that there are some Edegrad or RMS prop, or you can just use explicitly scheduling. Yes, and so there are some ways how we decided how the learning rate is changing. Okay, so, and as a function of your learning rate, what you can see in the training of the neural network, you can see the certain different values of behavior of your loss function. Yeah, so this is a nice example of typical loss. So it's going down on average, but you see it's kind of wiggling up and down for the very large kind of network. And you say this network is 100 of epochs, but even 100 of epochs for the large problem is nothing. It's several thousands or hundreds of thousands of the epochs. And if what you see is how the learning or how the loss is behaving, so if your loss is going down, like exponentially, you can think, it's going down first fast enough, and afterwards, slowing down, it seems to be a good learning rate. If it's going down fast, but afterwards plateauing, it means that your learning rate is a little bit high. If it's going down too slow per number of epochs, it means that your learning rate is probably low. And if your loss is increasing, it means that yes. So you need to probably decrease your learning rate, because you're exactly getting out of that parabola, or kind of that of the possible minimum. Okay. And again, so we need to also check what is the learning rate vs training error. And as I mentioned, we can do the shadows for the learning rate. So kind of reducing learning rate every time when the validation loss stagnates, for example, or you can have your learning rate is going down, and afterwards it's plateauing, and you decreasing the learning rate. And as you decrease the learning rate, so that you can recognize more features in your energy landscape, so you can get a better convergence, and so on and so forth. Okay, so that's one part of the pieces which you can play with. So you can choose the different optimizers. You can use some adaptive learning rates. You can have a learning rate shadows. And when you're training real large problem, that's what you need to play with. Kind of like this is your degrees of freedom. So, but that's far not all degrees of freedom. So now we'll talk about the activation functions, because we are talking about the sigmoid. But the sigmoid is not the only choice. So simple naive choice, you can replace sigmoid by the function which behaving like a sigmoid. And this is tanh(x) function, which is looking in a very similar way. And this is also legitimate activation function. Yeah. And both of them is kind of like, why do you want to replace the sigmoid with something that the gradient of the sigmoid is often nearly zero? Yeah, because if you calculate the gradient somewhere here or somewhere here, it's nearly zero. Yes, because what the gradient is the change of function. Yes, and the change of functions here are zeros. And we need to have a gradient of our nonlinear function, although we can calculate it analytically in advance, but we still need to afterwards substitute the value for the training points to calculate the amount of the gradient. And that what will give us not good. Okay. What shown to work nicely is something just called ReLo activation function. And it's a very simple function. So it's a linear function for the positive axis and 0 for the negative axis. And you would think that, oh, but this is a linear function. But because the linear function is a combination of two, or because this function is just combination of two functions, it becomes a nonlinear function. And the gradient here is very easy to calculate, yes, because it's just two straight lines. But it works quite nicely. Especially it works very nicely for the internal layers. Yeah, and there is no analytical proof, but there is a numerical proof. So if you take the same neural networks and you use for the activation function tanh and ReLo, and this is, I think, a snapshot from some paper or sigmoid, what you will see that with ReLo, you are training much faster. So and that's why for the ReLo, for the internal activation function, for the internal layers activation functions. And that's why it's very often used by default a ReLo. But ReLo is not only choice. So to find this 0, you could have another linear function on this side, but with a different factor. So here is just, y is equal to x, and here is y is equal to ax, but such that it's not 0, but it's going down very slow. So that gradient here is not 0, is a constant, but not 0. Okay. So as you see, the ReLo is a standard choice. And again, there are trade-offs, and you just need to do experiments. And the numerical experiments will just show you, that which functions works better for your problem. And if your problem is not standard, you might want to deal with the old choices. And if your problem is standard, you need just to use the wisdoms of the crowd and see what works for other people. If you just do, for example, image classification problem for whatever classes of images you are dealing with, or you're doing some text processing problem. Okay. So okay, so what we can also do with weights. Yes, because what I haven't told you is that, we will need to calculate the derivative with respect to the weights and update them using the gradient descent or stochastic gradient descent or some other ways, or whatever the algorithm we choose. But we need to choose some initial values for those W's. And kind of like simple choice is just choose zeros, yeah, because why not? But in fact, it's a very bad choice, because what does it kind of like what is the intuition, or even just to take them identical. So if all the weights are equal initially, the gradients will be also equal, and it will be kind of very often it will be zeros. So, and there are different ways of strategies. So, people do, they can use some, random numbers to initialize the weights. For example, here they use one type of Gaussian number. There is another type of Gaussian number. You can use them where the mean is dictated by the dimensions of your system, or you can use the uniform random numbers and so on. And you see just, how the training goes. Okay, so there is another thing which you also need to do with weights to prevent them from growing, overgrowing, or undergrowing, is something like, similar to what we were doing with the regularizations of linear model. So during learning, sometimes, kind of these weights are shifted, and they shifted sometimes, they can get some drift and shifting. And what you can do, you can, while the training, you can add a little bit of normalization to your weights, so that if the weights are shifting, there is some drift, you can just put them back to some normal value. And this is called batch normalization. And again, from the practical perspective, it's just a standard layer in the PyTorch or TensorFlow. You just, you add this layer, that layer, plus batch normalization. And again, so there are some experimental evidence, so to say, or numerical evidence of that, how good accuracy grows with and without batch normalization. So essentially, batch normalization works, and one's supposed to use it. Okay, so again, one can also add a good old regularization. So we can use L1 or L2 as before. Yes, again, so you see, you have a lot of options, and that's what also makes partially the training of the neural networks difficult, that you have a lot of design parameters which you need to train, and you need to find the systematic way of how to do it. Okay, so there is another little bit counterintuitive concept, which is called dropout, which also works extremely well, and you have to have it for, for the image classification and things like this. So when you need to scale it, and what is a dropout layer is just you add in a layer which randomly on each bout of training will zero out certain percentage of the weights. And the question is why it could be useful. And it could be useful because of the very simple idea, so that if you have some, by some randomness, you have some drift in the values, so that, there is only part of the values are learning something, or the part of the layer is learning some information. If you do the dropout, you essentially zero out that information, and you force the layers to learn all the layer to learn the information which you need to learn for your neural network. And that is why the dropout, again, it's a standard layer which one have to use. Okay, if you don't have to use it, but if you will use it, it will increase your it will increase the efficiency of your neural network in recognition of whatever you want to recognize, or prediction, and it's also will increase what is called the generalization ability of the neural network, because you learn one and the same information using the different paths within your neural network, roughly speaking. Okay. And essentially, yes, you have an input layer, you have a hidden layer, and you add dropout layer, and you see here with probability 50%, essentially, that every training round, half of the neurons are zero out. And you would think that it's extremely stupid idea. But in fact, for example, for the image classification and things like that, it works, and it works remarkably well. Okay? So yes, intuition that it's a form of regularization, that it's encouraging that the information is learned in the whole layer, not in the parts of the layer. Yes, and one could think that it has relation to ensemble learning, and it's intuition. But the reason why we can say all of that is just because it works extremely well, and that's why we can try to figure out the intuition why it works. Okay. Drop out at the test time. So yes, so naively you can stop dropping neurons and see what's happening. So we can go through that. So we can play with the dropouts, and we'll see it in the tutorial. And the last bit which we are going to talk about is this situation. So how long are we going to train, and where we're going to stop, and so on. So what you can do something which is called early stopping. And what is early stopping is, so if your training loss is going down, and your training loss will always going down as long as you're training more and more and more. But what you can see that the validation loss is going down, and afterwards, plateauing and going up. So when essentially what is clear from this picture, that you don't have to do all of that, somewhere after step 50, you don't need to do already any training, yeah, because we are good enough. We're already overfitting, or going to the way of overfitting. So all the, again, standard packages, they support this option of the early stopping. Okay, so this is one option. The second option is related to the fact that there is always not enough data. And what you can do the data augmentation, because usually, and we're going to see it with the MNIST. So what it is, so you get a handwritten digit, which it digitized, yes, which means that it's an array of numbers between 0 and 1, because it's kind of, it's a gradient, shades of gray between 0 and between white and black. So it's a number. And from the point of view of the program, it's just an input array. So, but from the point of the human, you know, if you take that handwritten 0 and shift it a little bit, it's still written 0, yeah? Or if you rotate it a little bit, it's still 0, not on 90 degrees, but on 5 or 10 degrees, it's still 0. But from the point of view of the matrix, it will be a different matrix. So essentially, based on the one handwritten digit, you can produce, you know, 5 or 6 extra digits. And that seems to be, this is the way how the people do data augmentation. So you can add shifts, you can add, sometimes if it works, reflections and so on. So again, so it works. And by the way, speaking of the neural network architectures, so there are neural network architectures which are taking that automatically into account. And they are called the equivariant neural networks, or kind of or geometric neural networks, because what they are taking into account automatically, so that you can take your input data array and you can arbitrarily rotate it and information is remaining the same. Or you can, so essentially you can, on the level of the neural architectures, you can incorporate symmetries. And of course, in that cases, for that architectures, you don't need the data augmentation, and it's better trained from that perspective, because it's not only have a rotation on, you know, on the 5 degrees, it's have a rotation on 1 degree, on 2 degree, on 2.1, 2.2, 2.3 degrees, and so on till infinity. Okay. So yes, and there's a nice example of the data augmentation for the image. Yes, so if you have a cat, you know, you slightly rotate it, it's still cat. You reflect it in the mirror, it's still cat. So whatever we do, we crop it a little bit, it's still cat. So we can do essentially, you know, from the one image, we can produce 6 images. So we can increase the size of our data set 7 times. Okay, so, and that's, we're slowly, I think, coming into the convolutional neural networks. Okay, so if we're talking about the images, the question is how we represent the images on the computer. We just represent them as grayscale images, as a 2D array, yeah. And if there's color image, it's a 2D, it's a 3 2D arrays stacked on top of each other, yes, because each layer is for each component, yes, which are called channel, red, green, and blue. Okay. So this is a typical example of the image from the MNIST, or handwritten digits. Yeah. So in these images, they can be kind of they can be used for the classification. So when we can use it for the data augmentation, and you know, one should be careful with the data augmentation, that we still convinced that this is a 3, this is a 3, but you know, when we come here or here, it's already not so clear. Okay. So sometimes what you want to do in the images, you need to detect the structures of the images, and that's what the modern networks can do. And if you detect the structure, it means that you can shift it easily. So if we know that there is an object, we just, as long as we're not cutting the object, we can use the same image. Or, as I mentioned to you, that in those geometric neural networks, you can incorporate the symmetries, so that you can incorporate the translation invariance or equivariance. Okay, so what else one can do with images, or kind of what will be the structures which we need for the convolutional layer? So, or what is a convolution? So we can use the information about the images in the previous layer and do something with these numbers to produce one number here. For example, we can do the pooling layers, and we can pull it like this. So we take every square of the 2 by 2 and take a maximum, and this is called max pool, or we can do the average. And using these tricks, you can create some structure, okay? And what we do with convolutions, we're going to see just now, because we need to apply some filters, because we're doing something, but what we do, it would be clear. So what we can do also with images, we can do an operation which is called convolution. And what does it mean? You know, it's written in this formula, but roughly speaking, what does it mean? We take a filter, for example, this thing, And this thing is defined by, you can think about that this is a matrix with the values, yeah? And these values will need to be learned by the network on some stage. And what we can do, so we can, if this filter is looking like this, we can now apply this filter to each part of the image, sequentially moving this filter over the image. And the way how we apply it is looking like a formula like this, but essentially it means that we take all the entries for the image and we multiply it in the same way, and we produce some other image. So this is the image which is produced from this one by applying this filter. And the idea with the convolutional neural networks, but that the form of this, the neural network is going to learn in such a way so that it helps the recognition process. Okay, so there is some formulas which explain how the convolution works. And again, as I mentioned, for those of you who's inclined mathematically, this is just, the kind of the special form of multiplication. Okay, so, and there are some examples, and, these kind of filters, and why we are all speaking about filters, that because before people invented these structures of the convolutional neural networks, so in the old days of AI, if you want to say something about this house, what was the logic? So we need to do something with the input image such that that something could indicate us some crucial features of the image. For example, this is example of the filters which detect edges. So if we apply the filter according to this rule, these filters to this image, we are going to get something like this. So everything is black except the edges. Yeah, so kind of like, and for many, many years, a lot of that ImageNet competition and things like that was essentially people were competing in designing filters. So, can we design a filter which can detect an eye? Can we design a filter which can detect nose? Can we design the filter which can detect, some other body part, such that, if you're detecting this, and that part, it's a face. And the beauty of neural networks or convolutional neural networks, that the filter design is happening automatically. Okay? Yes, historically until late 80s, the kernel parameters or filter parameters were handcrafted. There was edge detector. So can we design the kind of the edge of the three corners where the three edges means? Can we design where the four means and things like that? Can we design the filter which detects circles? But yes, the beauty of convolutional neural networks that the filters are learned, and only those filters are learned which are important for the problem. Okay, so now how it works. So we have a matrix with a learnable parameter. So we have filters, and now we apply the convolutional layer. So we have a filter, and now we go through the image step by step, and we apply the rule. Okay, and there are a couple of different games how you do it, because this original image could be filled up with zeros, and this is called with a stride of 1, or with a the stride means the step of 1. Sorry. Yeah, and you can get an image. Okay, so yes, the layer of zeros is called padding. Yeah. So, and you move it with a stride of 1, you apply the filter, and you produce the result. Here is a stride of 2, it means that you're moving by 2 in this direction, and 0 padding 1, meaning that we add to the image layer of zeros. And we produce from this image, or from this array, we produce this array. Okay, and this is the kind of the rough structure of convolutional filters. And if it's now seems a little bit exotic, don't worry, because it works. Yeah, so you can design the kernel size. Is this kernel 3x3 matrix, 2x2 matrix, and so on? What is a stride? How you move? Amount of zero padding, and the number of output channels. Okay, so and it's denoted usually like this, so you design the filter size, you have a input channel and number of output channels, and you create several layers. Okay, so and there are some examples, but again, what one need to understand that this is just, you just create the convolutional layers and you add them in and you do the training and it works. Okay, so pooling layers, as I mentioned to you, is just, there is a different types of pooling. So you can do the max pooling. So you can, if you pull from here, you can just put what is the maximum from the corresponding blob. So this is the application of the max pooling, but there is also average pooling, and one can think or design the pooling way. Okay, pooling layer, you can design how many cells you pull. Again, stride, zero padding, and the pooling function. Usually it's max pooling. Okay. Okay, so convolutional layers are translation invariant or equivariant. So if the object is translated, convolutional output will be translated by the same amount. And pooling layers are translation equivariant, and this is translation invariant. Okay, but they're both used in the architectures. Okay, so and now we're coming to the example of the very famous architecture, which is called AlexNet. And so that was the first architecture which beats all the previous machine learning models. And it's essentially started from convolutional layers, convolutional layer 11 by 11, and afterwards 5 by 5 convolutional layer, 3 by 3, 3 by 3, 3 by 3. And afterwards, so after all of this, and pooling layers, corresponding pooling layers, and afterwards fully connected layers, and the last layer, fully connected, but it have the output of 1000, and because the ImageNet have 1000 classes. So the last layer was doing the final classification job. And in each of these layers, you have a local normalization, you have pooling, kernel size 3, stride 2, no padding, ReLU activation, and sorry. First convolution, afterwards ReLU, afterwards pooling, and afterwards normalization. And afterwards you repeat it sequentially until you come here. And afterwards you take all of the entries here, you just flatten them up, put them to the full connected layer of the 1000 or 4000 neurons, another fully connected layer for 1000 neurons, and in the end, the fully connected layer of the 1000 neurons, where you apply just softmax. Okay, so usually it's denoted like that. And now you can easily download the pre-trained version of AlexNet and many other architectures and post-train them afterwards for your particular purpose. For example, if you want to use the AlexNet to do the classification of some other problem, which doesn't have 1000 classes, you can just get this architecture, kill this last layer, add your layer, and only train the weights on the last layer. Okay, so and there is a little bit outdated slide of the evolution of the neural networks. Yeah, so so as you see, as the number of it's an image class. So ImageNet classification top 5 error, and you see on the competition where the AlexNet went. So it was before, it was 28 to 25, and afterwards it's dropped almost by 10. And afterwards, it was dropping, but the number of layers in the architectures grows. So afterwards, after AlexNet, there was the VGG, afterwards GoogleNet, afterwards ResNet, and afterwards the precision gets so high so that there is no ImageNet competitions anymore. Okay, so and I think that's it, what I have for you for today in theoretical part. And I think we are almost in for the break, and we can have, if there is any questions, we can talk about them. And there was a question, is training neural network or is running neural network cheap? It depends on the neural network. Training is expensive. but I mean, for the large one, but if your neural network is large enough, running it, even just running it is also quite expensive. And if you are interested in that subject, just Google, what is the energy cost of doing the query to ChatGPT? So because you're not doing training because you're doing just running, but even that run is quite energy inefficient, and that is why everybody is keen on building a lot of nuclear power plant stations, because yes, in order to deal with these large language models, you need a lot of electricity. Okay. Okay, so I don't see any questions. Am I in the right chat? Yes. Okay, so let's do the break. Meanwhile, I will put the tutorial slides in.
Hi, Prof. We can continue.
Okay, good. So let's continue. Okay, so everybody should see in Canvas IPython notebook files. Yeah, so um, okay, so the first notebook is called PCA and clustering, but clustering we'll probably skip. Let's just focus on PCA, and I just show you how easy it is to use. And it will be also usage not only of PCA, but also TSNE. So there is a little bit of theory, but okay, that's not theory we had already. So what do we need to use? We need to use NumPy, pandas, scikit-learn, and from there we need to load dataset and decompositions, matplotlib, and we're going to do it for the iris dataset. And there is a little bit with a 3D plot. So from MPL toolkits, if it doesn't work, no worries. But this is just a 3D visualization of the dataset. Okay. So this is a data set of irises, the flowers, and it's a different characteristics of the flowers. And you need to decide, it's one of the standard data sets. You need to decide what kind of, based on characteristics, which subspecies of the irises you are dealing with. Okay. So we're going to use it to use exactly, to get exactly the insight into the usage of the PCA. So we're going to use accuracy score, ROC, AOC score, and okay, test training split and decision tree classifier. So standard thing which we've seen yesterday, we're splitting all the data into the test and training. Split is 0.3, and yes, random state, whatever it is. So because it's such a small data set, we don't print the characteristics of the data set. You can do it. So it shouldn't be too deep tree. So we can do it. We can check the accuracy score. So on the accuracy is quite nice, but we want it not for the accuracy or for the machine learning problem, but we wanted to see that we have 3 characteristics. Can we boil it down to 2? So, and it's done very simply. So we take decompositions. We say we want PCA and we want 2 components, because 2 components could be nicely represented on the 2D. And afterwards, what we do, so we just apply it to our data and we see how it's looking like, and we plot the corresponding components in 2D. And that's a nice thing about PCA, which you see immediately. You see it's kind of like, it's quick and straightforward, that we can see that, if we take that 3-dimensional data, which was here, and which, at least the way it was looking like, it's looked like all in kind of all into each other. So it's not linearly separable. By just applying simply PCA, we see that we get almost linear separability. We can definitely separate this class of the irises, and these 2 classes of irises are almost separated. And this word setosa, versicolor, and virginica is the types of the iris flowers. Okay. So, and afterwards, after we have applied PCA, we can check, how the decision tree classifier works, and the accuracy is improved a little bit. just because we see that, because it's much easier to take a decision. Because, for example, along this axis, everybody who lie in this side is this class, and along this axis, you need to be a little bit more inventive for the decision tree classifier. Okay. Okay, so now one can check, one can go over the components and see how much of the variance or how much of the data, roughly speaking, is explained. And you can see that the first component of PCA is explaining essentially almost everything. So that even it's in fact, it's essentially one-dimensional data. So kind of all of that in principles are boiling to the one axis. So if you rotate it in the right way, it becomes separatable along the one axis, most of it, above the 90% of the variance is explained. Okay, so now let's go into example, which is a little bit more difficult. Okay, sorry, what is that? Okay, so it's a question which is unrelated, but I can answer it. Does NITheCS CHPC have an in-house capability to build a supercomputer, in brackets quantum computer? You need to distinguish. We don't need to build a supercomputer. We have CHPC. We already have a supercomputer. But to build a quantum computer, the short answer, with all hardware and quantum programmers from SA, the short answer is no. Because to build quantum computer is extremely expensive task. And we don't have enough, I don't think that the South Africa have enough money for that, or kind of like there are more precious and important things for South Africa, and we definitely not have enough people to do it. I'm not sure what is the world quantum race. It depends what do you mean. There are different races happening, and it doesn't mean that South Africa needs to participate in every race. Okay, so let's go to the more grounded questions. So again, so we can now try to play the same game of principal component analysis on the digits data sets, and we already seen with you that it wouldn't work nicely, but let's see. So we can load the digits data set, and it's not a full data set, it's a part of the data set. And that's how the data is looking like. And now we can check what does it mean. So we can just plot some of the examples. And you see kind of this is very, very crude representation of the handwritten digits. Yeah. So it's it should be, it's 8 by 8. Yeah. Shape 8, 8. Yes. So it's 8 by 8 squares. So we have 64 dimensions, which are quite a lot of dimensions, because and this is also kind of trimmed down, because very often the digits data set is 28 by 28. Okay, so now we can try to do PCA. And don't forget that what we're trying to do, we're trying to project 64 dimensions in 2 dimensions. Yeah, because so that we can see and what you can see is, it's not very nice. I mean, okay, we can say that, we can separate this as a cluster 0 is separable, but most of the rest is not really separable. Yeah, so but again, nobody told us, that to project in many, many dimensions in 2D is always working nice. Nobody telling to us, nobody guarantees us, but this is a versatile try and see, okay, linear projection doesn't work, so we need to do something else. Okay, and I think we have something else here. Yeah, so and something else is one of those nonlinear projections, TSNE, which is stochastic nonlinear embedding. And interestingly, the interesting thing about the stochastic nonlinear embedding is so that every time when you run it, because it's stochastic, it's give you slightly different result. So let's run it. It might take some time, but you see it produces this usage of the nonlinear for doing the embedding, usage of the nonlinear transformation, give us much better result because we could clearly see explicitly clusters, yeah? So we could put the boxes around clusters up to, a couple of little mistakes. We can more or less we can solve, using this approach, we can definitely solve the classification problem. And if we run it, we might get slightly different distribution. No, it looks the same, strange. Is it because okay. So now we can try to do the same here and see, how good PCA is doing. I know. So we can now just check how many components we need to take in PCA to explain nicely our digits. Oops. And what we are going to see that is we need a little bit more components to explain 90%. We need 20 components or 21 component. So that's explained why, in 2D, PCA was not looking impressive. Okay. 20. Yeah, people answer the question how you handle the missing data. Now, it's not, the answer is not how you find that you have a missing data, but how you handle the missing data is a separate long topic because there are different ways how you handle the missing data. So you can just replace it with the neighboring values. You can replace it with the average of the neighboring values. You can estimate the probability distribution of your data and replace it with most probable values. So there are several strategies how you deal with the missing values in your data. Or you can just throw away the data which have a missing values. It depends how much data we have and what kind of problem are you solving. Okay. So let's go down. I suggest that we don't spend, you can play with the clustering algorithm, but let's skip it because this is just implementation of the k-mean clustering for some artificial created clusters. And you can see how many clusters you need to create and things like that. But I suggest that let's keep it for the self-study. Let's go into the neural networks. Okay, so any questions about the PCA part or just to clarify? A component is a combination of the features, like, yes, yeah, because it's not, you can imagine that this is just a rotation, that a component of the PCA is a linear combination of, in principle, all features. Because you can think about what the PCA is doing is just a rotation of the basis where you throw away certain basis vectors, which corresponds to the smaller eigenvalues or lower importance. So and that's essentially, yes, what it is in the nutshell. And that means that you cannot just throw entries or your features, because you produce new features with just the linear combinations. Okay, so now let's go into the digits classification first with the dense neural network and afterwards with convolutional neural network. So we need the NumPy, matplotlib, and the TensorFlow, and for those who want, you can use a PyTorch. Okay, so MNIST is again a standard data set which we can which we can load from MNIST, or you can download from somewhere else and convert it and load it in. But the cheapest way and easiest way is just to get it from the standard data set. So we need to take labels and okay, let's give a look on this. So that's how the data is looking like. So it's an array, yeah. So let's do 28 by 28, but it has its values from 0 to, in fact, 255, which means 255 means the darkest. It means black. But for the neural networks, we need to normalize it. That's why we're doing this bit. So we're normalizing it and reshaping our data set. The next thing, what we do, and because we are also loading, it's automatically, we don't need to do the test train splitting because it test train split it for us. But, we can load it to full data set and do it with a scikit-learn if we want to. So what we need to do, we need to convert the labels 0, 1 to 9 into what is called the categorical data. And so what we have training images, 60,000 images with the dimension 784, it's 28 by 28. Testing images, 10,000 images with the same dimension. Training labels are 60,000 training labels. 10. What does a 10 mean? Because when you convert to categorical, it's create a variable which is like an array of the 10 entries. And if you belong to a certain class, it will be just replacing it. And this is a vector of zeros, and it will have 1 to the corresponding class. So if it's 0, it will have 1 in the very first entry. If it's digit 1, it will have a 1 in the second entry, and so on till 9. We'll have a 1 in the 10th entry. Okay, and that's how the images are looking like. So we can use any other maps if you wanted to try, or we can change it. Okay, that's an interesting image. What's that? Is it 2? Okay, that's clearly 7. Okay, so we can plot it in a little bit fancier way as a little grid. Okay, so but now let's build a neural network. And here we're just going, because we're using the dense neural network. I mean, that's also, the images are looking like this, but for the purpose of this training, what we have done, we reshape it, this square 28 by 28, because it's a dense neural network, just into the vector of 784. So the model which you want to build is called sequential. It's got layer by layer, because you can have, you start with the layer and afterwards you have some branching. So that will be some other models, but if it's layer by layer, it's just very simple standard neural network, which is called sequential. And this is again, as simple as it gets, and we want to see, what are we getting for it? And as simple as it gets, what we're getting, we're just getting one hidden layer. Yeah, so we start from our input layer with our 784. Afterwards, we have a one hidden layer with 500 neurons, activation ReLU, and input shape is 28 by 28 multiply, so it's 784. And we're adding output layer, yes. The output layer with the 10 entries, because that's what we want to predict. That will be our 10 classes. And activation is softmax, because if it was a 2 classes, we would use sigmoid. But if it's a 10 classes, we use softmax. Okay. So we get our model. Sorry, because I haven't loaded the model. Okay. And we can build a model summary. And interestingly enough, it's automatically also telling us how many trainable parameters we have. Total parameters and number of trainable parameters. You would think that, it looks relatively small, but it's already have 400,000 parameters to train. So what do we need to do next? We need to compile the model. We need to specify the optimizer. And the optimizer is, remember, is what was a gradient descent, stochastic gradient descent. And as I mentioned to you, just Adam is another type of optimizer, also working very well. Loss. What is used for loss? Because we're doing classification. It should be some form of entropy, and the categorical cross entropy is what you use for the multi-class classification problem, because if it was a binary, it would be binary entropy. But for the multi-class, you use categorical cross-entropy. This is just a generalization of the binary entropy and matrix accuracy. So we compile the model, and now we need to do the training. Be careful on this step. If you don't run it on the Google Colab, your laptop might start thinking for a little while. So, and I choose a very, very small number of epochs, only 10, and the batch size is 256. Yeah, so it means that it's training kind of in the batches of 256 images or 60,000 images. And now we can run. Okay, so I just done 10 epochs, but kind of in the reality, for the real purposes, if when you train for the much longer number of epochs, what you will also add here into the model fit, you will have the early stopping conditions. You can also, because we here didn't have any dropout layers, so that one can play this game and see what are we getting. So now we can check what is accuracy. To get the accuracy, we need to do the model evaluate on the test data. And we get the test accuracy and the test loss. Okay, we get but I mean, even you see kind of like, even without any fancy steps on this data set, we get quite a high accuracy. We get almost 98%. So now we want to visualize a couple of things. For that, we need to grab a history of our training of the model. And the history is kind of like, we define it in the model properties. And we can plot the graphs which I was showing you on yesterday on the lectures. We can plot the training loss and the validation loss or test loss, because we don't here have a validation. And you see that the training loss is going down with the number of epochs, and the test loss is also going down, which is good. Which means that, in principle, we need to keep training, and that we still wouldn't get to the overfitting scenario. We can also give a look on the training accuracy and validation accuracy. Yeah, and we also see that, training accuracy is growing and the validation accuracy is also growing. Okay, so, and now what we can also check, whether we're predicting. So if we just need to not evaluate, but predict it, just model.predict, and we can check, what image is there and what are we going to predict. So for example, for index 120, we can grab the index 120, and it's telling us that the class is 5, which is correct, and we can play this game, for any other index out of the predicted out of the test set. We can do 900, for example. Oh, that looks like 1. Let's see. Yeah. So, and it's probably, it will take us few steps to find the mispredicted number. Yeah, and that would be also interesting to find who are in those 2% of the accuracy which are predicted wrongly. Okay, so yes, there is something which is called quantum machine learning, and it's about using of the quantum computing for doing machine learning. But we're not talking about that today. So have everybody able to run the notebook? Sorry? Mm-hmm. Mm-hmm.
I want to know, is it possible to like do kind of parameters search to know like bigger HTTP?
Yes, yes, yeah, of course it's possible to do the parameter search, but now you need to do this, because what you can do, for example, you see, because we have several parameters. For example, you can play with the batch size, and you can create an array of the batch sizes. Yeah. So you can have, 64, 128, 256, 512, or something like that. So you can have a range. And you could do it for any other parameters. You can play with the early stopping condition and things like that, and do some, parameter search. It's also work. Yes, of course, you can have a range of optimizers, because and again, if we just wanted to know what optimizers are supported, we can just do TensorFlow optimizers, and we're going to get a class TF Keras optimizers, and already from here we could see that we get the Adam as stochastic gradient descent and things like that. Oops. So, and you see you get the whole family of possible options, and you can choose whatever you like. But again, people have tried, and Adam seems to be working very well for this type of problems. This is very important. For this type of problems, that works well. For other type of problems, something else will work well. Does the training result not indicate significant and overfit? Why? Why do you think that we have a overfitting? Where is our? No, it doesn't. It doesn't indicate to us overfitting, because the test error is also decreasing. Test loss decreasing, training loss also decreasing. Why it needs to? Why do you think it's overfitting? And meanwhile, somebody have an error with trying to download TensorFlow. It depends, how you try to download TensorFlow and how you try to install TensorFlow. Christian, yeah, I also don't believe that it's overfitting, because you can easily overfit on this data, but on this data set, but we need to train for a little bit longer. So if you probably train for 1,000 epochs, you will see the overfitting, but not on the 10 epochs. Okay. You see, Christian, people are suggesting that you might have a wrong version of Python. Okay. So, and now we can do the same, but now with the convolutional neural networks. Okay, so it's essentially everything is identical, but the architecture of the network is going to be different. And now we need to maintain the shape of the images, because as we're going to do it with convolutional neural networks, we need to deal with the images as the square arrays, because when we do the convolutions and we do pooling, we do it with the local blocks. And that's where the convolutional neural networks are very good, because they are able to extract information which is kind of local information, which is contained in the pieces of your image. So we get, again, the same 60,000 images for the training, 10,000 image for the testing. Again, we have always the same handwritten digit. We can try something else. That is probably 5. Okay, so now we do again sequential model, but now we need to add convolutional layers, and we need to add them in the corresponding in the corresponding kind of step-by-step way. So, and what we're doing here, we're adding convolutional layer, and afterwards we're specifying the number of filters, the size of the filter, the activation function, and we have an input shape, because this is the first layer and it needs to know how many, what is on the input, and we're specifying that what we have on the input, we have arrays 28 by 28. Okay, and afterwards we're doing max pooling with a 2 by 2 filter, and after we're doing another convolutional layer with 64 filters, but with the same characteristics and the same activation ReLU function. And again, max pooling, convolutional filter or convolutional layer again. And after this convolution, we can do max pooling if we want, but we don't have to, or we can do something else. Because we also, I haven't added here batch normalization layers. I haven't added here dropouts. You're welcome to experiment with this. But now, after we have done enough convolutions, what we wanted to convert it to something which could be used for the classification. So we're flattening the layers. So it means that instead of having this, what will be the output after here? It will be a bunch of filters, which you can imagine like a 3D array. And now we need to convert that 3D array just to the straight line, because we need to add just, a fully connected layers. So we're adding fully connected dense layer with the 64 neurons, ReLU. And afterwards, we're adding an output layer with the 10 neurons and with a softmax again. Okay. So the first observation is that, okay, we get a more involved network, but we get much less parameters. Yeah, because we have over the neural network with one hidden layer with 500 neurons, and we have 40,000 parameters, and here we have only 93,000 of parameters, which is in principle better. And that is another thing, that is a kind of nice thing about the convolutional neural networks, because although we have a much deeper structure, the thing is that because we apply one and the same filter, and it's parameterized by the one and the same set of parameters, that allows you to have a much smaller number of parameters. Although when you do it large scaling, you still have millions of parameters. But if you do it like with a fully connected layers, that will be absolutely untrainable number of parameters. Again, all the rest is the same. Optimizer, loss, metrics accuracy for the accuracy, and we do the number of epochs again 10, batch size a little bit smaller, and we do the training. And what is happening? Why do neural networks suffer from vanishing and exploding gradients problem? Because when you've seen which neural networks, the deep neural networks, which have many internal layers, because when you calculate the gradient using the back propagation, you need to multiply many matrices, roughly speaking. And if the entries of those matrices are very small numbers or numbers which are above 1, what you get when you multiply many small numbers, that number is quickly going to 0. When you multiply numbers, which are above 1, that number is quickly exploding. And this is your problem. And that's why, you need to take it carefully on what kind of number you multiplied. So, and that's where it's coming from. And that is one of the problems, for example, of this time series or kind of the language processing models. The first family of them was called recurrent neural networks, because over there you get even more multiplications. And when it was converted to the more advanced structures, which are called LSTMs, one of the things how they managed to fight that problem was exactly just by forgetting certain multiplications, roughly speaking. Okay, so let's do prediction, history. Yes, and what we get here, this already are looking much more than, that one can start to argue on whether we are dealing with overfitting. Because here we can see that the test loss is a little bit up and down. Okay, so we can play the same game. And what was our accuracy? No. Yeah, so we get a little bit better accuracy. Yes, so we get almost 99%, 98.8%. And in previous example, it was 97, yeah? 97.9. So we're a little bit better with the smaller number of parameters. But, you know, kind of that will be exactly the convolutional neural networks will be the structures which are very good for these problems, exactly because you are learning information about locality. So you kind of, because you do these filters, you are learning some information about what's happening in this part of the picture, what is happening in that part of the picture. And that's why, you know, they will be very good in capturing that structures. Okay. So essentially, yeah, just do the experiments. And what I suggest that you do, guys, you just try to, you can try to make it better. And you can try to make it better by adding layers here or in this notebook. Maybe try to add batch normalization, dropout layers, and see what's happening. And also try to see what's happening when you change the dropout percentage. Okay, so let's try and doing that. And I will monitor the chat in the Slack. Okay, so Slack is quiet. Honestly, I don't understand the question. In the contents of supervised learning, explain the bias variance trade-off in details. In how many details? I think I've done it yesterday. And if something is still, if you still have questions, let's do it like this. Yes, where's my... So I think that the ChatGPT can do it better than I. Would you rather recommend DNN or reinforcement learning for optimization? Stop. I mean, you need to understand what problem are you solving. For the optimization of what? What kind of problem do you try to solve? Because the tools which you're going to use will be determined by the problems which you're trying to solve. Because dense neural networks or any other neural networks, as the feed-forward one, they're solving prediction type problems. And reinforcement learning is solving the other type problems. It depends what problem you're talking about. Oh, yes. And somebody gave a very nice resource of the book written by Nielsen. Yeah. So, how successes of adding in new layers? How success in-house? Bad. Why? Mm-hmm. Sorry? I don't know what is extreme machine learning. You know, people invent many words, many terms, you know, because extreme might mean different things, you know, on the very large scale. For example, you know, machine learning on the very large scale will happen in South Africa on some stage when they're going to finish to build an escape project. In that case, it will be machine learning on extremely large scale. It's already happening at CERN. They're building in some machine learning algorithms in their data processing. So, but I don't know in which sense also somebody can speak about, extreme machine learning in which sense. So, chat is quiet. Okay, so 3 layers produce these results. Okay, good. So 3 layers of what? Okay, add Kira's 512, you add in. Okay. So you just added 2 more dense layers, but that's boring. You see, kind of like you added 3 more layers. You probably the number of your parameters have grown. I mean, it's good that you've done it. So the number of your parameters have grown drastically. And you don't need to specify the input shape. Okay, so. But it's interesting to add those layers which are non-standard one, like batch normalization layer or dropout layer. So what do we need to do? We just need, for example, take this architecture, and add the layer here. Yeah, so kind of we need to add first dropout and afterwards batch normalization. So how we are loading it in? So we and so here's layers. And now let's see. So I want to add, where is my dropout layer? Yeah. And let's see which variables. It's probably just need to take them. So something like this should work, I assume. Yes, I should. Because I think it's just 0.5. Yeah. So this means that half of the. Yeah, let's try and see. Oops. Why? Okay. So maybe we need just to redo the model. Okay. Model summary. So I just added 1 dropout. It doesn't change the number of parameters. Okay, so let's see what we have here. Yeah, it makes it a little bit because that was 8 on previous one. Yeah, I think it was 988. That's 989. Okay, so it's probably marginally improved. But the problem is that of course it's already so good that it's difficult to make it better. Okay. So and yes, one can keep playing this way. So you guys you see it, yeah. So what is happening in the chat? Nothing is happening in the chat. Okay, so okay, so I get a specific question about what to use, and I hope I can say it. Yes, yes. So the question is that we need to find the moving particle, but I mean moving particle in where? So what is input data? Optimal scanning pattern. Oops. Okay, so that we have done. So now we can give a look on all of these things. And we see that now it's a little bit, the test loss is a little bit, yeah, behaving. I think it's behaving a little bit better. It's less wiggling. Okay, so let's put the dropout everywhere. Or at least also here. And in principle, of course, we don't need to use 50%, but 50% usually works well. And we can afterwards also add, okay, again, I need to reinitialize the model. What is the use of using, oh, this is an interesting question, a pre-trained model such as whatever to train your own model? The use is very simple, you know, that even for that AlexNet, which won, you know, competition in 2012, so it was, you know, a very long time ago. I think for them, it took something like a week to train the model on the one GPU, on the two GPUs, but I mean, it was not a GPU cluster, it wasn't, but, you know, modern image recognition models, it takes weeks to train on the cluster of GPUs. And if you have your own cluster of GPUs, of course, you can train it from the scratch, a very large model. But most of people do not easily have access to the cluster of GPUs. And that is why, you know, if you have your model, which know how to do the training already, kind of know how to recognize the typical features, it's easier just to took away a few last layers and add train them. And even more, in the yesterday, I mentioned this large language model DeepSeek, which you can download locally. Of course, you can do the fine tuning with the OpenAI on the OpenAI website, but you know that costs money. But you can take the large language model, like a DeepSeek, you can download it, and you can train it because it already knows how to speak English well enough, and it knows enough information. But you can add training on your given data. So it wouldn't be kind of, and you can create a kind of a more narrow purpose expert. And afterwards, what you can do on top of that is called distillation. So you can really, like, you know, create a large language model, for example, which is very good in certain domains of knowledge. So, and that's why you want to use pre-trained models. And the latest version of that DeepSeek, it was first used in some sort of, you know, a generic large language model trained with the company, and afterwards it was used in reinforcement learning to improve its accuracy. But, you know, again, it's all hours of the GPU cluster time, and unless you have access to it, but it's also, you know, just don't forget that it just simply costs money to train models. So that's why, you know, usage of the pre-trained models is a very useful thing. And you in particular ask mobile NetV2. I don't know what is mobile NetV2. Okay, good. I was told that but what is it, the graphical model? Or yeah. It's like image. Okay, good. Does batch normalization typically have to be earlier in the layers? If I apply it after dropout, it makes loss way more wiggly. Okay, so what was the batch number? You want to add the batch normalization just, I think, after the convolution layer.
Yes.
What it was in the AlexNet? Let's give a look. In AlexNet, it was activation. No, pooling, and no, normalization was after pooling.
Okay, that makes sense. That's good.
Because there is convolution, ReLU activation, pooling, normalization. Now, but I mean, the fact that if the loss is wiggly, I think it's not a problem, but it's just a little bit of you just need to look on the generic trend of the error. Is it possible to use machine learning in civil engineering? Of course, it's possible, but it depends for which problem. You can use machine learning everywhere where you need to deal with where you have where you can formulate it as a machine learning problem. It's possible to use if you have certain classes of optimization problems, it means that you can use machine learning for that because machine learning will be the best optimizer. It will be the better than the out-of-box standard optimization things. It just depends on the problem. If there is a way how to solve the problem by analogy or by something like that on multiple examples. So if you can formulate it as a machine learning problem, it means that you can use it, and you can use it in any domain. So let's add batch normalization and let's see what's happening. That was a training with the 2 dropouts, yes. Oh yeah, let's make it 99. So it's dropouts. You see, it's really improved. And you see, it's make the test loss to go much less overfittable. So now you see in real time the importance of the dropouts. Although one might think that it's a very counterintuitive idea, but it works. Okay, so and where we want. No, but in that case, we want normalization before the max or before the dropout. Yes, because we first need to normalize and afterwards forget. Let's see. Do it on the Google Colab. No, but I mean, are you using it on the Google Colab or not? Do you have a Gmail? Go to the colab.google.com and run it over there, because also your computer might cooks while trying to. So what we want for batch normalization, and the batch normalization is coming, I think, without parameters. Yeah. There is no parameters for the batch normalization in the flow. Yeah, there are some default parameters, but I think we don't need to specify anything. Okay, let's see where we are. Okay, I again need to reinitialize the model. Okay, same number of parameters. Very good, Benjamin. Google is a good answer. You can also suggest ChatGPT. Okay, so let's see what's happening to our batch normalization. And if suddenly one of the layers are making things worse, it means that we just don't need to use this layer, because again, the problem which we're now dealing with is quite small. So in many problems where some fancy things are required is, when you do the scaling, when the stuff gets bigger. Okay, so I don't know how it make it a little bit worse or something like that, but let's see how the graphs are looking like. I think they look pretty similar. So at least in my case, but maybe because of my dropouts, my batch normalization doesn't make it much worse. Natasha, have you been using the batch normalizations for the yeah, okay, there is also an answer, but I mean, have you used it without dropouts? So you started with the batch normalization. Can do it again here. And we can. And let's see. What a contribution of machine learning in predicting natural disasters. Many natural disasters are unpredictable, and some of those are predictable because machine learning is not a kind of it's used in kind of in weather prediction, but some things are working well, some are not. It's like it's a very generic question. Oh, how it's used in civil engineering, or how it's used in prediction natural. It's very generic questions. It's like you need to be more specific, and in that case, you can get a more specific answer. Okay, so I see that about the about the batch normalization. Yes, I mean, what you need to think about that, when you need to have why you need to have a batch normalization is when you have such data so that that your values begin to get some shift. So maybe we're still in a very, very small network with not too large values. So that's why, it's maybe it doesn't help in us at all. But that's why, yeah, dropouts, you see dropouts helps, but the batch normalization is not necessarily helping. Okay. So we see that it's improved a little bit. Also the batch normalization on the second layer. And yes, our test lost, I think, is also wiggling nicely. Okay, and so that's how you do it. You make an experiment, but the only difference compared to what I've done, you need to do it separately and record the results. And you can play with early stopping and things like that. Okay, okay. So have anybody was able to do the same thing which I have done to add dropout and the normalization layers and train the model? Okay. Somebody saying that this training is still running, but if your model is running slow, in that case, what you need to do, you might want to do the same thing on the Google Colab, which I already mentioned. Because if you have a Gmail account, it means that you have a Google Colab access. Yeah, and in Colab there is also GPU, but there is also not your CPU, which are still good enough, so that your local laptop wouldn't be cooked. And the address is what is it? Colab. So yes, and over there you can do stuff on GPU for a little while. And what else can I show you? What other experiments can we do here? I don't know. What can we do here? So in principle, one can play with the data augmentation, but that we need to do on the earlier stage, because these numbers we can clearly rotate a little bit left and a little bit right. Or one can try to do the same thing for the other data sets. So we can try to do it not for the MNIST. Which data sets do we have? Okay, no. Yeah, see, this is CFAR 10 and CFAR 100. This is a subset of the data set which is used in the ImageNet. Yeah. There is a fashion MNIST, so where you need to recognize the elements of the closing items. Okay, the Boston housing, California housing is just a housing price, so this is not CNN problem. IMDb is for the recommender, probably. And Reuters is probably text data set, yeah. So what do we want to try? Okay, yeah. Colab is, yes, is running better, yes. And in the Colab, when you choose the, what is called the instance, you can choose GPU. And I think they can give you access for free for, I think, for a couple of hours every day, every 24 hours, something like that. Of course, they have a paid plans, which you give you better access, but for free, you can get it also for a little while. So let's, so guys, try to do the same, but for the fashion MNIST. And the fashion MNIST is a data set where there are closing items, and let's try to do it for the fashion MNIST, okay? What are our local successes?
Something else to be.
I see that it doesn't look like.
But I'm going to wait for them.
Good. Yeah.
Say it doesn't work. Just are you in that environment here? This is like on the system.
So, okay, this is balance, yeah?
Yeah.
So you have Python in the system Python.
Yeah.
Okay, but the problem is that this is also bad thing to use it. What you need to use it, you need to use to install miniconda and play in that one. Because if you mess up your Python in the system,
Yeah.
you will need to reinstall lines. Just install miniconda, not the full miniconda. Install miniconda and you do it there. Because also, what is your system Python? Sorry? Yeah,
3.12.
3.12. Ah, but the people were saying that there might be problems with the TensorFlow with the Python.
Yeah, I remember I did that. 3.7, there's some iterative clause that like breaks a lot of collaboration.
So it's the latest version of
No, but you see, that's why, even if it's slowing down, I prefer to use miniconda and things like that, because, in that case, if I mess up everything, I just kill the folder. I can install a new miniconda. Now, you kill environment, yes, you can create environment, and if you mess up completely, you can reinstall miniconda, but it's at least it's problem-free experiment. Sorry? Now, sequential means layer after layer. Yeah, you can add as much layers as you want, because if it's exactly the architecture function.
So
Why you need to separate? Because in principle, what it allows you to do, it allows you to have not layer after layer, but you have layer, and afterwards you split it to the two layers, and you have a two collections, and afterwards you merge. So but sequential means just layer after layer. So it means you have the first input layer, and you need to say to model what is the input share. 28, 1 chunk, 22. And afterwards you adding layers after layers. So for example, you add max pooling, and for the intermediate layers, you don't need to specify dimensions because the system knows by itself. And the problem is that if it's hard to calculate, it will be quite involved. There are formulas which were also in the slides, which is more you to calculate what is exactly how many output size and so on. So you are max pooling, you see now when we add another layer, we don't specify.
no, it's it doesn't like that
It's the number of
part
filters.
of the conditional.
So kind of like it's created.
Kind of wants you to put it as a separate thing.
And it will choose those filters and treat them. So it will be the convolutions and the layer of the filter number 1, number 2. So it creates a bunch of layers like that. And so as a result, what you have here like a three-dimensional long matrix, which you now want to use for some classification, organised that we want to use for the app training last bit. So that's why what flattening is doing, you just take this 3D and convert it to the one. Because flattening is a standard thing, standard command, which is just converting stuff from the most dimensions to the one dimension or square if you specify dimensions in flattening. And you add dense layers. And the dense layers are just fully connected layers. Like, every layer is whatever the number of guys here will be fully connected to this 64. So it will be all connection.
Doing this shape here.
Yes, and afterwards you add in the outer layer, which is also dense because it's a fully connected layer. But you already said that you need only 10 neurons because this is around 10 neurons where you're going to read out the class. And in order to get who is who in the readout class, you use softmax so that the program is written all the 10 classes.
Rather than having the input be from figure. To try that.
Let's see what's happening in the chat. Okay. I see that in the chat there is a progress with the MNIS. Good. My prediction seems to be using numbers from before. How do I fix it? You need, there should be something where you have a description, because of course your classes will be still numbers, but there should be somewhere a translation table between numbers and what the textual meaning for the classes. Because and you need to check how many of classes we have in the MNIST. So we might have more classes in the fashion MNIST. Let's do it like this. Okay, so let me save this notebook and let me duplicate it. Yeah. Okay, so let's run it. So now here we need to use fashion MNIST, and we can still call it MNIST because that doesn't matter. Okay, so now let's see what are we dealing with. Train data. Okay, so arrays, good. 28 by 28, good. So let's see what do we have in the test data. Oops. So this is a tuple. Okay, now that's interesting. What will be now a test data? So this is array and class. Okay, but where can we get? So what is so because this is definitely our classes. Yes, it's a second bit. So maybe we need to give a look how the fashion MNIST is built in TensorFlow and see. Because I would like to get the titles or names of the items, because the classes will be still numbers because we cannot do it with text. At least, anyway, when we do with text, we convert it into the numbers. But okay, okay, it's also 10 classes, and that's so now we can see the classes, and now we can check whether the answer in the so prediction 8. No, I think it looks wrong because this looks like a Snickers. So it should be label 7. It depends how it's ordered out. Yes. Yeah, if it's from one, yes, yeah. That's one need to check. Because it might be correct. Okay. Okay. Okay, so let's do it like this. No, this is the wrong one, so we need to do it this way. So okay, so this is our classes. Good. And oops. Okay, so this is our training shapes. Tupus also here. Okay, okay, good. Now I see. Okay, now we can just remove this. So this we already done. Yes. We just no. Let's use the same notation so that we don't need to change too much. Train images. So this is X train. Test images. That is X test. Train labels. It's a Y train, so that we don't need to rewrite everything. Okay, test labels. Okay, let's redo it. Okay, and now we can do this and it's supposed to work. Yeah. Okay. Okay. And we can check. Nice baguette. Yes, that's our classes. Or that is our images. So we can just try. Okay, let's do it without all of these guys. As the first step. And let's see what are we getting. Okay. So yes, the image from the chat with the training and test loss. Yes, the test loss is growing quite wildly. Yes, so it means that there is some issue. Yeah, I think it's also validation loss seems to be a bit higher than we had with the MNIST digits. Good, that means that there is a space for improvement. Okay, so I think my one looks a little bit better than that one which was in the chat. Yeah, my one definitely looks better. And we can also turn on all our additional layers and check what are we getting. Okay, prediction 5 and 5 is Sandel. Okay. Prediction 0. Okay, this one looks better. Yes, prediction 0 teacher. That looks better. Okay, but I mean, clearly here we can train probably for longer, but it just takes a little bit long time, okay? Oh, see, it looks quite nice. And it's obviously the indication that we can keep training. Okay, so we can try who's 120. Wow. T-shirt. And that looks like a T-shirt, yeah? Where is my chat? Yeah, 0 is a T-shirt. Try some other index. Oh. 4. Who is 4? Code. Okay, that could be seen as code. And so on. And one can continue that. Okay, somebody is asking question whether the neural networks are similar to Markov chain Monte Carlo simulations. And yeah, how to put it? I think it's not a very correct question. It's an ill-posed question in the sense of Markov chain Monte Carlo simulation is the way to simulate is to solve something. It's a numerical technique. And while the neural networks, is like what neural networks for prediction of something could be seen probably as, you can compare, but if it's some sort of unsupervised algorithm, you cannot compare it because Monte Carlo simulations and think about it's just a different thing because Monte Carlo simulations do not require examples to learn. I can run Monte Carlo method for example without Markov chain Monte Carlo, but just Monte Carlo method for example to calculate the value of the number pi. Yeah, so I can just do the circle and just throw the random points into the circle and afterwards count how many points are outside and inside, and I will get the value of the pi with a very high precision. But I don't need, there is no kind of learning process here at all. So you cannot compare these things. It's just the different numerical techniques for the different purposes. And for some purposes, you need Monte Carlo, and for other purposes, you need neural networks. And in one of the previous editions of the coding school, which have the videos also on the NITheCS website, you can check. We had a speaker called Uwe Jackel, who was exactly explaining some Monte Carlo methods. But it's really kind of just the different things with the different purposes. Both are useful, but for the purpose which they're built for. And in fact, they can be even for certain properties, they can be used together. For example, just out of my head, recently people realized that it's, for the certain problems in physics, in particular for the problems in many-body physics, when you need to estimate something which is called ground state or ground state wave function for the very complex model, you can use neural networks as the sampler of the as the probability distribution for the states. But the procedure by which you are estimating that probability distribution of that neural network is by using certain Monte Carlo schemes. So in principle, it's not even, it's just the different techniques which can be used together, or it could be used separately for the different purposes. Okay. How are other successes? Because we definitely know that in Porch, we have some successes. Do we have successes somewhere else? Okay, but that was even a little bit boring because we have the same number of classes. Okay, that's okay. So but the chat is completely dead. What's happening? Important. Okay, no, but that's why you need to use the Google Colab. If the important TensorFlow takes so long, it means that you definitely need to use Google Colab. Because that should work better. Okay, somebody have, but you haven't got an accuracy of 90% over which data set? MNIST or fashion MNIST? And having accuracy 90% doesn't mean anything. Okay, for fashion data, okay, good. Okay, but that looks nice. It means that you can, in principle, you can train longer. So your training and test loss curve, you can just increase the number of epochs and see how it's going, because so far it's going quite nice. Okay, but nobody's seeing the chat. Okay, but I'm getting what am I getting? Okay, I'm getting 90%, roughly speaking. But clearly, I can also be training more, but let's not waste full compute of this machine. Okay, so in that case, I will also upload this code into the canvas. And someone who was complaining about the use of the TensorFlow, have that person managed to do it with a PyTorch? Or he don't try? Ooh, test accuracy 99%. So, and how's your test and training loss graphs are looking like? And how many epochs have you done? So someone get a 99% accuracy. It's a good question. Yes, is it for the handwriting or fashion? Okay, so there is no response, but okay. But again, you shouldn't be aiming to have a 99% accuracy because, you know, if it's very super high or if it's one, you know, sometimes you just don't know how it's generalized. So you need to take it like, you know, you need to train good enough and use it. Sorry? It's good enough for your problem. You decide by yourself what is good enough. For somebody, good enough, 80% will be good enough. You know, for some problems, it could be good enough. 80% could be very good. Or it's 90 or 99. It depends, you know, what are the stakes in the problem and how much it will cost to you from going to 80 to 90, from 90 to 95, because it might be that, you know, just doing every step. Okay. Yeah, 89, yes, seems to be good out of the box. 90, yes, looks like, okay, 20 epochs. Yeah, and you can see it's still doing well. One can even try to do more than 20 epochs and see whether that, because, you know, this a little up of the test loss might be just this training epoch. And if you keep training for, I don't know, 30 epochs, you can see whether it's continuing to rise or not, because it could be just local wiggling. Good, good. I mean, you know, you see, I also get what 89 or 90 just out of the box, and that's supposed to work if the training happening. Very good. Okay. Any other success stories in the chat? There is no local successes. Still working on the import for TensorFlow. Yeah, you see, that's a problem. Yeah. Okay. I think we need to slowly to wrap it up because some of you probably wants to go for the lunch break. Aluwani?
Yes, Prof. Thank you. Let's end here, and then you can take some questions on the chat, and then we can resume at 2 o'clock for the closing ceremony.
Okay. Okay.
Thank you, everyone.
Okay. Thank you, everyone. Yes, I'll still be in the chat, so ask your questions if you want to. But if you are still doing something and it's taking too long, just try to use the Google Colab. It might be slow, but not as slow as your local laptop, because also that could be a partial issue.
Hello? Are you ready? Vet Cam, can you hear me? Okay, so it's fine now. It's done, right? It's tested. Okay, sure.
Hey, Benjamin, can you hear me?
Hi, Verna. Yes.
Hi, I can hear you. Good, good.
Sure. Because I don't want to be late. I need to open. Can you open, unmute, camera on? Camera's on. Yeah, yeah. Okay, is it working?
Hi,
It's not
Alawani,
working.
can you hear me?
Hi, can you hear us?
Yes, I can hear everyone.
Okay, fantastic. Okay, is my camera on?
No.
No, okay, let me go to my office. Sorry, we've got a technical something. I'm just gonna go open another call. I'll quickly open up and I'll be online in a sec.
Alawani, can you hear me now?
Yes, yes.
Well, I can. Can you hear me?
Yes, Mattia, I can hear you.
Excellent.
And I see you have my name. Maybe you can rename it. I think you're using my account for the login.
Yeah, I'm feeling quite honored to be named Benjamin. Maybe I will just keep it. Now let me update.
Let us wait for Renee, maybe to connect.
Also Krishna as well. I don't see Krishna here.
Hi, Krishna. Can you hear me?
I think you have to make him a panelist. He's in the attendees.
Okay, okay.
Nee, Leeuws gaan ons baie goed saamvat, nee.
Werner, you're unmuted.
Okay.
Okay, hello everyone. It is 2 o'clock. Am I correct if I say hi Mattia, hi Werner, Alawani, Benjamin? Let me see who else is here.
Hi, Renee. Yes, good to hear the voice.
Okay, Deepika, can you hear me?
Yes, we can hear you.
Okay, excellent. Thank you. Benjamin, can we start or should we wait a little bit?
It's fine. I just want to check where Krishna is. He's attendee. I just wanted to get him.
That's fine. Okay, we wait a minute.
He is here. And Daniel said he can't make it, but somebody else was going to represent
Okay.
from Northwest Potchefstroom. So
Okay, we give it a minute.
yeah.
Are the participants online already? I'm just not
Yes,
sure.
yes. I
Okay,
see.
everybody's online. Okay.
Yeah, I
Good.
see everybody's online. Maybe should we start?
Yeah, go ahead.
What do you think? Yeah. Okay. Can I go ahead?
Yeah, go ahead.
Okay, excellent. Thanks. Okay, Krishna. Okay, this is me. Oh, okay. We need to give him access. Okay, let's quickly make Krishna. Let's just quickly. Sorry, I didn't realize. Okay, I see there's two. I'm just going to promote to panelist. Let me make the other one. Okay, Krishna, I've made two there. Okay. Okay, is that done? Wonderful. Okay, Krishna, welcome. I see you here, right?
Yeah, I'm here.
Excellent. Okay, can we go? Okay, I see we are recording. Okay, so thank you very much to everybody being online here. I would like to thank this wonderful participative effort. There are many universities, many people, CHPC, NITheCS, all these universities, everybody involved to make this school a huge success, and every year goes from strength to strength. I want to start by thanking everybody on the side of the CHPC, Benjamin, normally Bernard, everybody, Christian, everybody that used to be at this. I'm thinking also of Daniel, that used to be CHPC, now at Northwest. I mean, there's so many people that have given impact. Also Alawani and Tutukile on the side of NITheCS, all the champions. This is a phenomenal effort. I've had many discussions with people that tell us of the impact and how this is helping them. So on behalf of our director, Prof. Francisco Petruccione, I'd like to thank everybody for this effort. And in conclusion, I want to encourage people that if you are not yet on the NITheCS email address, please do so. Go onto our website, nithecs.ac.za. If you're not there yet, please do so, join, so that in the future you can get amazing initiatives that that gets advertised on our platforms. I want to give opportunity now also to Werner and Benjamin to say a few words, if Alawani is here as well, just so that we can all have a few words in closing. Werner, would you like to go?
Werner, sorry, Bernard, let's just go through the presentation. So the
Perfect.
various,
Yes, yes. Okay,
then
sorry,
we'll-
sorry. Perfect. Okay. Yeah, sure. Thank you.
jumping the gun. Just
No, perfect. No, I appreciate it. Thank you.
That's
Perfect.
a lot to cover. All right. So yeah, again, I'll repeat the sentiments that Renee mentioned. So yeah, again, this is the closing session for Coding Summer School. A few things to cover in our agenda, but I just want to start off with a lot of video showing everyone at the different venues. So let's just play that. Thank you, everyone. So hopefully everybody has fuzzy feelings now, all the memories for the past few weeks. So let's move on to the agenda for the closing session. So again, this was a huge effort from everyone, all the universities, to get together and make this all work. It's a lot of effort. Started over 6 months ago, more than that, just to get all the venues and all the champions logistically getting everything organized, and then obviously the students to come and participate. I really appreciated all the students that actually attended in person. You've all made, you know, the Coding Summit School worthwhile. So let's move on to our agenda. I'm going to cover a few items, just briefly look at the objectives we covered for over the past 2 weeks, get a bit of feedback from the CHPC, NITheCS, some feedback from the champions. Most importantly, we're going to do some prizes, some prize giving, and then what happens after Coding Summer School, post CSS, and then finally end with a thank you. So first, let's move on to you know, some of the objectives we tried to achieve over these past 2 weeks. So everybody has seen these timetables, you know, quite a lot, and you've all been inundated with a lot of information, and your brains are full. So hopefully something will stick. But just to cover broadly what we've covered in week 1, for example, we covered coding practices, data pipelines, Streamlit. I think that was probably the favorite for week 1. A bit of Jupyter, some web scraping, some Bash Lab. A lot of students had fun with it as well, and then map observations as well. Right. So just a brief overview of what we covered in week 1. And then week 2, presented by NITheCS, very important topics that were covered: computational thinking, probability and stats, and machine learning, as we ended off today. So key skills that hopefully everybody could benefit from and could take, you know, useful, you know, aspects from it for their own research moving forward. And again, this is, you know, if this is new content to you, this is only the beginning. You have to, you know, continue to learn and grow in various other courses, other coding summer schools, other, you know, courses you can do. This is one step. You have to always carry on and grow and see how other people teach these topics. All right, so that's your brief overview of the objectives we tried to cover and topics. Now I just wanted to get a little bit of feedback, maybe from the CHPC and NITheCS again. So maybe Werner, just a few words from your side.
Yes, just get my camera on. Yes. Thank you very much, Benjamin, for this 2 weeks. And I can just say on behalf of CHPC, there's a lot of effort that goes into it. I think it's been said a few times, but I don't think people really realize how much effort goes into this. And when we look at the CHPC component of this, which is mainly the first week, I can say without hesitation that the bulk of that effort goes with efforts from Benjamin. Of course, normally has assisted him extremely well, but when it comes to the decision on the content, the preparation of the content, Benjamin, yeah, there's no doubt that you have put in a tremendous effort. And I think everybody will agree with me that Benjamin doesn't just see this as another task that he has to do on his, say, KRA for to perform well in his work. He has a deep passion for this. And I know this because in preparation for this, even during the summer break, he was still developing and expanding the quality of this content. And I'm sure that by attending this, you would have picked up on his passion to do this stuff. And Benjamin, yes, that is the first person I just want to thank very much. Thank you very much for this effort. It is truly seen. I think it's appreciated by everybody that's participated in this. And I can say now already, I know that in the feedback that we will get from the surveys, this will probably also be very well reflected. So thank you very much. I want to thank Normally that has assisted you directly with so many aspects. And I cannot even claim to know everything. I unfortunately could not join much of the Coding Summer School this year, but I know that there's dedicated effort. They've been traveling, going to the different sites, even to see how the participants are doing. So Normally, thank you very much to you as well. And then I just need to comment also, an event like this does not just happen. We don't just decide it will happen and then this year we host it. This is the culmination of many years. And I also want to reflect on our close collaboration with NITheCS. NITheCS is a key partner. So Renee, I don't know whether Francesco is on the call, but I must just say we could not have done this in this format with this impact without NITheCS. And we have been doing this for many years, and it has gone through many transitions. I think I mentioned in the opening session, I mean, initially we started off, the CHPC did its own thing, NITheCS did its own thing. Later we combined our efforts and it became a hosted physical event where only a limited number of students benefited. Then we hit COVID and we had to do this in a virtual way, and that really honed our skills on how to develop and present content in a virtual way. And then we took the step after COVID to have it in this format. And I think this is really where the impact of this training took us to the next level, where so many more people could benefit directly from this training. So I want to thank NITheCS for helping us in this process to put this together. And then, of course, we cannot do it if the champions doesn't step up and put up their hands and put the practical things in place, the venues, the catering, engaging with the students at your different sites. Thank you so much for this. I think we as CHPC and NITheCS are benefiting from getting our content and what we want to train to such a vast audience simply because you are taking the practical steps to make it possible. So yes, thank you very much to all the champions in this effort. And then lastly, the participants. I mean, it will not help if we put all of this together and the participants doesn't participate and learn from this content that is presented. So thank you very much for your participation. And I want to encourage you, please give us your feedback. We are not saying this training course is perfect by any means. We would like to hear where are the things that we still need to improve, what do we still need to do to make it even better. So please make use of that surveys that you will be getting opportunity to fill out and let us know. So yeah, thank you very much. I'm really pleased from a CHPC side. I mean, I see this as when we look at all the training events that CHPC is involved with, I see this as the top one. This is the one where we reach the broadest audience and where we really have built up, I think, now a momentum that I'm very pleased to tell everybody about. So thank you very much. Thank you very much, Benjamin, once again, and also for the opportunity for me to just come in and say a few words. I'm gladly gonna stay tuned in to look at the rest of the program. But yeah, with that, handing back to you, Benjamin. Thank you very much.
Thank you so much, Werner. Renee, from your side or anyone else from NITheCS, any further words?
Sorry, is Olawani here? Olawani, I think Tutukile is traveling. Olawani, are you here?
Yes, I'm here.
Okay.
Yes,
do you wanna say
thanks,
a few
Benjamin.
words? Thank you.
Yes, I just want to thank everyone and Benjamin and Normally for pushing and doing all the hard work. And most important to our champions for organizing all the venue, like Werner said. No, that one is I thank everyone, and also maybe just to also mention to the participants that we thank you also for engaging on the Slack, and yeah, we had a great one this year. Thank you.
Thank you so much. Thank you for that, Olawani. Benjamin, over to you.
All right. Yeah. So just to reiterate, I mean, this is from NITheCS side. Olawani Tutukele really went a lot of effort to get the champions on board and make sure everything is running at the venue. So I want to thank a huge thanks to them as well. It's a huge feat getting all the universities, on board and at the same time, collaborating. So it's a huge feat and very unique, definitely in South Africa and probably in the world as well. So just be very proud that you are part of this. I would now like to move on to the champions. I have a few that we want to just get some feedback from. The first and foremost, I want to just let Mattia give some feedback from his side, and also he's a director of e-research at UCT. He hosted, the event for us at UCT at the library. So I just want to give him a chance as well, just to get feedback from his side.
Hi, Benjamin. Can you hear me?
Yes, go ahead.
Oh, great. Should I also show some slides, or would you like me to do that later?
You can do some slides if you want. I can stop sharing if you want.
Right. Okay. No, because I was well, I did prepare a few slides
Yeah,
about
go ahead.
about useful training opportunities and useful tips for attendance if we have 10 minutes, but I didn't know
Yes,
whether you
no.
want me to do that now or not. Okay.
You can share them if you want to.
Great. Thanks. So let me know when I overextend my welcome and when I run out of time. I don't want to keep people from their relaxing weekend.
Sure.
So,
If what, 5 minutes or so, if that's fine.
okay, great. I'll do that. Okay, so in terms of feedback, I mean, I'm afraid that besides, I mean, checking the course content and taking a quick look at the champions channel, I didn't have much of a chance to participate this year. It's been busy at the beginning of the semester. But what I can certainly say about the content is that I very much like the interaction and the more collaborative portion. I think that has been working much better. I mean, when it came to student engagement. So I commend you, and I certainly encourage you to think about how to do that more engaging the next time around. Here, I just wanted to suggest, I mean, a few things. I mean that the students that attend this, I mean, can think about in terms of further work and further training, I mean, as they go forward. And in order to do that, I mean, I recycled some slides from my job as e-research director at the university. So e-research, courtesy of ChatGPT, for those who haven't come across this term, is a loose term, I mean, for digital research technologies and skills. So it's a term that was coined in Australia and that UCT adopted, I mean, about 10 years ago when it set up this research center. And the idea is to use advanced information and communication technologies to do better research, better, faster, and more impactful research, in my word. And so why did we come across the idea of e-research, and why is it getting all the more important to do e-research properly? That's because, I mean, the world has changed. I mean, the world of data and, more recently, the world of artificial intelligence has changed dramatically fast. And it's changing at breakneck pace, as university administrators and students know all too well. I mean, there's always new tools and new tricks, I mean, that you can have, and yes, a new way to trick the system, if you like. So one has got to get even all the more smarter and try to adopt, I mean, new tools and new methodologies in a large number of areas. So artificial intelligence is one thing. I mean, trying to find out how you can best storage, manage, and share your data, but also your software with colleagues and how you collaborate with colleagues, particularly on large international collaborations, has become all the more important. And of course, I mean, the world has also got smaller and flatter, so there are opportunities for engagement, every week, every time of day. So how do you choose, I mean, what is relevant to you? How do you actually get access to the services and to the skills that you need to thrive, I mean, in your own profession? And I'll skip this because we know that, data is getting bigger and it's also getting more complicated. But more importantly, data is pretty much worth nothing unless you use it properly. So for all you can say about artificial intelligence and the advent of big data, you need to be able to manage it and also to chuck away, I mean, all of the useless data and only focus on what counts. So this is perhaps, I mean, one of the best skills, I mean, for data scientists and for any informed citizen, really, in the modern age. So when I talk about big data, I mean, I often think about what happens in my research in radio astronomy, and this is a quick plot of how the typical size of a data set in terabyte has changed over the past 20 years, 25 years since the beginning of the century, and how it is changing, I mean, at a breakneck speed, driven by radio telescopes on South African soil. As you may know, I mean, the Square Kilometre Array is in the process of being built in South Africa, but we already have a fully South African telescope up and running, which has been producing petabytes of data over the past 6 years or so since its inauguration. And this is only going to get, more trickier with the advent of the SKA phase 1, which is going to take this into the exabyte scale. So similar challenges are also coming to the fore in bioinformatics, Earth observations, and pretty much any science that relies on digital technologies, on digital cameras and digital data taking. So it's useful to understand, I mean, that e-research and big data services are really a collation of different services that are provided by different actors across the university. And this is just a picture of what this looks like at UCT, but you get a feeling of how this is going to work at different universities. So the research office needs, I mean, information and data about the university. Faculties need to be able to manage their students and also to do research. The IT department is always struggling to keep up with the growing needs of the community. The libraries historically have provided support for data repositories and publications and data sharing, and they are getting more and more into the business of digital technologies. And of course, I mean, the research enterprise at the university is thriving, I mean, because of the adoption of these new technologies. So in this respect, I mean, I caution you not to make too big a thing about big data. I mean, there are still lots of things that are not driven by AI. So ChatGPT is not going to solve your problems. I mean, you will still need to know about research methodologies, research ethics, how you deal with personal data in particular. You will still need the soft skills of working with collaborators around the world, even if you have the best collaboration tool available. You need to make your name known out there, so you need to keep an eye on your visibility and on sharing, I mean, the output of your work, whether it is in public article, LinkedIn posts, or actual publications. And of course, I mean, small data still matters, and data is not just data anymore. You also want to be able to access it real time. So maybe it's data that is not saved, but that is just looked up in real time. And you also need to understand hardware and software in order to be able to use it properly. And of course, any data must be fair to be of use, which means that it must be able to be found, accessed, interpreted, and reused. So what I suggest, I mean, particularly if you are undertaking a research career, but also if you are undertaking, I mean, a data project of any kind, is to think about your research project in a holistic manner and try and develop skills to tackle the different steps of the research project life cycle. And I won't bother you with the details, but I mean, planning is always overlooked, is often overlooked, and trying to identify the tools that you're going to need to do a good job for the kind of project that you have in mind, for the kind of scale of data problem that you're going to have, is always important. And when you get to the end of the project, I mean, you very often have the temptation not to close it out in a sensible manner, not to publish all of your findings, not to provide all of the supporting data because some of it is messy. And I caution you, I mean, to resist this temptation because in the modern day, I mean, having access, I mean, to well understood data and being able to reproduce other people's findings is not only how you learn and how we verify research, but it's also how research progresses. So it's crucial that we don't lose track of this important role of digital tools and of scholarly publishing. So how can you learn more about this? I mean, e-research again is a tricky word, and perhaps you're better off talking about digital research skills. Here I have some tips, and I'll make sure to share this in the course curriculum if Benjamin will allow me to. But fundamentally, I mean, do your research, and obviously starting by Googling and ChatGPT and things, but definitely you will come up with a short and eventually not so short list of useful tools from anything related to creating a data management plan, accessing different science gateways or high performance facilities, accessing, the Langaro cluster at CHPC if you're involved in research or industry research, and different research data storage tools, which here are specifically indicated for UCT, but you also see a number of tools that are publicly accessible and accessible by researchers from across the country, like Figshare, the DIRISA data deposit tool, and the Zenodo digital repository at CERN. Last but not the least, I mean, don't forget about software repositories that are, industry standards like, GitHub, GitLab, and the like. And don't forget about the more research-specific identifiers and and research publications, the repositories, because these are the ones that you're going to need in order to find out about the previous work. And so combining scholarly publishing resources like Scopus, Web of Science, and Google Scholar with software resources on GitHub and GitLab, I mean, is going to actually get you farther, much faster. Last but not the least, I mean, often there's a problem about getting started and not knowing how to, well, pick, I mean, the best resources out there. I'd encourage you not to be too reckless and too impatient. I mean, definitely start, I mean, with resources that your university provides. I mean, if you're still in a university context, but definitely ask GPT what are the best self-training resources for developing digital research skills. I did this morning and I didn't bother to copy the output, but obviously the clearest and most interesting resources, I mean, came up, I mean, from Coursera to individual resources within the universities. But something that is never quite emphasized as much as it should is that asking your peers and creating communities with them, but also asking slightly more senior people that have gone through what you have been doing this week, I mean, not long ago, is always very helpful. And often, I mean, in the wealth of information that you have on the internet, you forget to do that. This is also important because as well as mostly young researchers and young students, I mean, you have the opportunity to create communities within the universities and within, well, the big South African worldwide internet, so that you can actually sit down with them, whether remotely or physically, and actually develop, I mean, a better understanding of the skills that you would like to develop, and creating connections for the future, for your future work and for your future career, possibly in research, possibly in the industry. And throughout, I mean, always keep an eye on how good is good enough for you. I mean, because that will depend on your professional and personal goals. There are some good resources about good enough practice for scientific computing. But whatever your goals, I mean, keep in mind that increasingly continuing professional development, so taking time off to develop your skills and to understand, I mean, what the next big thing is going to be, I mean, in the digital workplace is going to be key. And again, asking your peers and slightly more senior people cannot be done too often, because that's how, I mean, we used to learn, and we have sort of forgot how to do that, particularly after COVID with this new digital new world. So I'll leave you here. I'm sure I've overextended my welcome as I feared, but I hope that was useful. And well, by all means, I mean, drop an email, even if you're not at UCT, and I'll and do look up, I mean, our website if you're interested in some of the services that we mentioned. I mean, we have pointers to lots of services that are not only UCT provided at UCT, and I'm always helpful to clarify the content of our web pages or provide feedback to others if I can. So thanks again, and have a nice weekend after the end of the school, and keep in touch.
Great. Thanks so much, Mathieu. Really appreciate it. Very relevant, content you covered. So really appreciate that insight that you gave, and we'll definitely share the slides. We're definitely going to share the slides as well with everyone. So thank you so much. Just moving on to our last champion, just to get feedback and any advice as well. If you want, Krishna. Krishna's been with the Coding Summer School for many years, longer than I have. So Krishna, from your side.
Okay, thanks, Benjamin, and thanks to all of the CHPC team. So everybody that did all of the hard work to put all of the stuff together. I know what it entails. I've been there and done that. So it's not easy, but thank you to Benjamin and Normally that did a great job of putting all the material together. And also from the NITheC side. There were some great lectures on the NITheC side as well. And I think the students did benefit. It was an intense 2 weeks for most of them. You could see a lot of tired faces. But people have learned things. And my suggestion to you students, please remember, we gave you all a baseline to actually work from. So I would suggest, you'll notice in a lot of scripts and things that we've given you, you can actually just take the same thing and reuse it for your own work. I may be manipulated here and there just to get it to work for what you want, but you have the base. So please definitely go through the stuff and make sure you actually practice, because practice makes perfect. If you don't keep practicing, you're going to get lost with the coding stuff. And basically, when you start, you're going to start afresh again. You don't want that to happen. Nowadays, everything's about data, right? So make sure you use the data well. And then just to say thank you to all of the champions. I know how much effort it takes to actually put everything together, because I'm on that end of the spectrum now. So, and then also just make sure, guys, those of you that are champions, must just approach other faculties and things. I actually found it quite useful this year to approach the electrical engineering department, and they agreed to actually give me venues for the event. So that helped. So just so that we can get sort of, you know, other departments involved and more people, instead of you being like the one person representing the whole university from one individual department. It just helps with organization and everything else. Right. And then generally, there's not much else from my side. Just thank you again, everybody, and thank you for actually attending the 2 weeks. It was long, but I hope it would all pay off. And on a last note, I remember Prof. Ilya at the end was saying that your machine usually will lag with the TensorFlow. So just for those of you that don't know, you actually can get access to CHPC. So just speak to your supervisors and they can organize, because it is free access to the CHPC where you can run your models much quicker than that. Yeah, that's it. Thanks, guys.
Cool. Thanks for the plug in there, Krishna, for the CHPC. So definitely that's very true. All the ML stuff you saw that Prof. Ilya was showing, you can definitely run it on there, our CHPC Lingao cluster. Okay, so moving on to the more fun side is the prizes for this year. So let's have a look. Prizes. Okay, so I'm first going to hand over just to Renee, just to again, just a big shout out to the champions. These are all the venues that were actually had, you know, venues with students attending. So just hand over to you, Renee.
So thank you very much to all these people that assisted. Some of these names are very well known, people that have been very long associated with NITheCS, and there are also some wonderful new names here. So thank you very much. And we know that it's taken a lot of hard work. And so we'd like to, as you know, we partner with CHPC. So what we're going to do is to organize vouchers, a small token of thanks to these champions, to say thank you very much. We know that the work you do far outweighs the token of thanks, but the benefit at your university is huge, and we're very grateful. Thank you for so much. And soon after this school finishes, we start the next round. And like somebody said earlier, each year it grows from strength to strength. So we can't do it alone. This is a group effort, and it's truly phenomenal what is being achieved here. So thank you to everybody involved here. Thank you so much.
Thanks, Renee. There are a few universities actually missing here, so apologies for that, but we do appreciate all the hard work you have done. Okay, so moving on to the next part, which is the top students. So again, for top students for this year, these are the Pythonista Awards. These are students that have excelled in the attending the classes in terms of being active, you know, with the content, you know, doing well with the quizzes, and also participating in Slack. So it's an all-round, you know, prizes that we give students. And again, these are exclusive book vouchers, 500 Rand, that each student gets. So, okay, here we go. The top students for this year are from UCT, Zusipe Masale, Botuso Pale from BITS, Coelho Ledwaba from Northwest from Poch, Lindiwe Mapala from UJ, DFC campus, and Oloa Makinde from Timber Lab. So well done to all those students. It was an effort to kind of find, you know, the best students for this year, again, as it always is. But again, well done to all of you. I really appreciate the effort that you put in. So again, well done. We'll be in contact with you with further details for your prizes. Well done. All right, so we have 2 more prizes to give out. So before I present the next 2, Streamlit was quite an important part of the previous week, and that forms basis for our following prize. But I just wanted to give you a bit of an overview of some Streamlit apps that many students took on their own and made it, something fun for themselves. So they a bit of a creative way to express themselves with their own research pages and maybe little apps that they can create. And it's super quick to create your own web applications with Python using Streamlit specifically. So I'm just going to showcase a few nice examples that people have used, that they have shared. So this is Dr. Oxman's research areas. He created this one. And then we have Zen Perry as well, profile page that he created with Streamlit. Then we have Sakila as well, created a profile page over here. And Trevor as well created their own research page. So these are all just allow you to create your own profile that you can share with anyone at any time. Just makes it easy for students to create that. And here's another one as well from Zoe, very nicely done with a lot of pictures and little emoticons. So all these are on the Streamlit channel. So you can have a look at that in the Slack on the Streamlit channel. You can have a look. There's another one as well, also very well done, presented by Felicia. Well presented. So, really impressed with all the work that everybody's put into, creating your own research profiles. And then some people had fun with Streamlit as well, created little games as well. So somebody created a little game. You could toggle a switch, and then there appears a little, ghost, I guess. So yeah, people are having fun with Streamlit as well. Very easy to create these applications with Python using Streamlit. Somebody created a Noughts and Crosses game as well. Quite impressive to what they've done. Somebody created a leave days application to just record the leave days. You can see the category is already tied for the year, and then you have to record the reason. You can input your microphone and record the reason. I guess you should sound sick here as well if you want to, if you're for sick leave, and take a picture of your surrounding just to make sure you are truly sick. So this is quite a fun example somebody created. Somebody created a DeepSeek login user account creation page as well. Have a look at it. It's on Slack. Quite interesting. This is kind of my favorite one. Kelo Buhile created a bachelorette overview. She had a lot of pictures of herself to kind of promote, to apply to date to the bachelorette. So very fun Streamlit app that she created. She has certain preferences I can see on the Streamlit app as well. So if you want to know more, look at the Streamlit channel. You can see a page. There. But going to the Streamlit Award again, it was tough again this year. A lot of good effort went into it. But the winner for this year is Sarah Burnett from University of Pretoria. She created an excellent research profile page, quite detailed, went quite into a lot of extra features and widgets in a profile page, and she also created another page for the Coding Summer School Report, another website, web app, which summarizes all the content for the Coding Summer School, which is excellent. And you can see the different sections that she's done. So again, well done to Sarah Burnett from University of Pretoria, for the effort as well to creating these pages. And then to our last prize, our Slacker prize. So the most active participant on Slack, and as you would have seen, the chat channel on Slack is very busy, over 6,000 messages and more on Slack. But there's one student that was most active, and that is Javeria Makta from WITS. More than 214 posts as of today. So well done to you. You also win a prize as well, exclusive books, gift voucher for you. So well done to all those prize winners. Really appreciate all the effort that you have put in. And I think that's all the prizes for that we have to offer you. But again, I guess most important prize is all the content that you have learned for the past 2 weeks, and all the interactions, most importantly. So lastly, what happens now post Coding Summer School? Again, Slack will stay active. CHPC and NITheCS will post some upcoming events just to keep you busy. We'll give you feedback on, code alongs when they happen. But again, as the other, lecturers mentioned, to continue your Python journey, your research journey, and to learn from others and grow. Next up from CHPC will be the winter school, where we train you in HPC and using the Gao cluster. Also, the CHPC National Conference will be at the end of the year, so please look out for that. From NITheCS, the mini schools happening all the time in colloquium, so we'll share those details and much more. And that's all. Just keep learning. There's so much more to kind of learn, and just keep growing. And yeah, that's it. That is all from my side. And just want to thank everyone for attending. And I'll just end off with the video that I played earlier, and that'll be all. Thank you very much, everyone.
Sorry, Benjamin.
Alwani, go ahead.
Oh yes, can I quickly maybe share also a slide from my side? Just
Yeah, sure.
a minute. Yes, I won't take much of the time. Yeah, we've got token of. Can you hear me?
Yeah, go ahead. Yeah.
Yes, can you?
Are you breaking up a little bit?
Is it fine now?
Yes, all good.
Oh yes. I just want to thank everyone as well. And also we've got a token of appreciation from NITheCS. And then this goes to a voucher of 1,000 rand, exclusive book voucher, and then this will be given to Normally for all the hard work she has done, and also the second person is Sue Benjamin. Yeah, so thank you very much.
Appreciate it. Appreciate all the effort.
Alawani, and also we'll arrange for you and Tutukile also, because you guys, all of you, are the backbone, like Werner said earlier. It's phenomenal what a handful of people taking hands with many others could do so that our community can benefit. So thank you so much to all of you.
Thank you.
Cool. Thank you, everyone. I will finish with the video again.
Thank you.